So can you, I've given you 5 minutes to install and call the program. If you are done, then we can start. So yeah, you're not hearing me because I'm not talking. Okay. So how many people have installed the programs and have called them? So we need Agricole, we need Dubai, we need Latte. Some of them we may not use them. We need effects we're going to use. We need Malcolm. We need ggplot2. We need a car library. Okay. So the first thing that I want you to do is please get the somebody say, would you please give an example? The variance in the analysis of variance is a pool variance. So if you already installed this program before, then you only need to load them now. You don't need to call them anymore. You don't need to install them, you just need to load them. So once you are done with the with loading the programs, then we can start off. But it's important that you set your working directory where the data is where you should set your working directory. So I will request all of you to go to, there is a menu called session. You go to session. From session, go to set working directory, and then choose a directory. The scripts are already shared in the files of yesterday. But I can still get for you the script from my desktop. No, we cannot share material directly on emails. There are very many people. The links are provided, please. Okay. So can we now go ahead with the analysis? How many people have installed everything so that we can start? Install and loaded the programs. Done 1, 2, 3, 4. Okay. Okay, good. So what I want us to do now is we go and change the working directory. So ensure you know where your data is. So go to session, set working directory, and choose a directory. Okay, have we set working directory? Can I see in the chat how many people have set their working directory correctly? We don't want anybody to remain behind. Okay. Okay, good. So after when we have set our working directory, then we can go ahead and start the process. So we start from line number 13, which is Latin square. So what we are doing here is we are reading, we are using the program read.table. Why we are using read.table? Because we have our data is in a form of a text file. So here you're saying header equals true. That means the heading should be read from the data. So you can use read.csv if you're having the extension .csv. So let's run this line and see what will happen. So after running that line, you will see that in the global environment, you see Latin square here, 25 observation and 4 variables. That is what you will see. Have you succeeded in calling the data? How many people have succeeded in calling the data? Yes. Okay. So the next thing is we want to see what are the names of the variable in my data set. I click on this. So you can see here, we have rows, we have column, we have treat, we have yield. So that means we have 4 different variables, as you can see from there. You can also type in the console and just type DIM, which means dimension, and then type the name of the file, Latin square. It should tell you that the dimension is 25 by 4. James, you're saying no. No, why are you saying no? What is the no for? Jackson, can you type what you raise your hand up, but can you just type what the problem is? Okay. Now, the next thing we are going to do, we are going to look at the structure of the data set that we have, the data frame that we have. So you put cursor in line number 15, and then you run. So here we can see that it's a data frame with the 25 observation of 4 variables. We have row, which is an integer, 1, 1, 1, 2, 2, 2, 2, 2. We have column, which is also an integer. Then we have treat, which is the character, and then we have yield, which is numerical. So that is what we have already there. Okay. But remember, if we want to do analysis of variance, we need to create what we call factors. So in our case here, the factors are in our model, the factors take care of the design and the treatment. So we need to convert row into a factor. So what we do is we go into our data set, we pick the column that we call row, and we substitute it with the same column, but this time we converted it into factor. And then we also label the factor. We have labels there: cow 1, cow 2, cow 3, cow 4, cow 5, and cow 6. So that is what we have. So we can run factor. So we can then run, also convert the columns, and then we can also convert the treatment. So the next thing that we need to do is we need to check the structure. So we're going to check the structure here. So it's still a data frame. So now row now is a factor with 5 levels, and they have cow 1, cow 2, and so on and so forth. And then column is also now a factor with 5 levels. We convert to factor because when we are doing the analysis, we need to R needs to recognize these variables as categorical variables. If it doesn't recognize them as categorical variable, it might go and start calculating their mean, their variances, and so on and so forth, or might include them into the model as quantitative variable, and yet they're not quantitative variables. Okay, I'll try to zoom in. Okay. Okay. Now, before we do that, I want to create a column. I want to create a column. This was not in the command, but I want to create another column. But this column here, we are going to call it data points. So what we are going to do, we are going to have, let's say we are going to have data point. This one now you type it now. Data point, I'm going to create it. I'm just going to make it a 1 to 25, just number 1 up to number 25. So this is a simple command that I actually say data point 1 to 25. I have this. I can run this. What I'm going to do now is I'm going to modify my data set, which we call a Latin square. So we are creating a new data set. And with this data set, we are going to combine the data point with the previous data set. So we can say cbind. And then we have data point. And then I bring my Latin square here. So I want to create the first column that I call data point, so that my data now gets, instead of having 5 columns, 4 columns, I'm going to have 5 of them. Let's run this command and see whether it will work or not. Okay, so I can check by looking at the structure of my Latin square. Okay, so now you see, now we have 5 variables. The first one being integer 1, 2, 3, 4 up to 25. If I look at the names now, if I calculate the names, the name should be, you see now we have data point, we have row, we have column, we have treatment, we have yield. So I've decided to add one particular point because somewhere down in my command, in my I'd change a little bit of things. So what we are going to do now is, I don't want to have the old names, the old name of that row, column, and treatment. I want to change the name. This time I want to have, the first column is going to have the name data point, which is fine. The second one is going to have cow. The third one is going to have milkman. And then the last one is going to have feed, and then we are going to have mirror yield. So we are going to do that. Okay, so let's try to run this and see. We're trying to change the names. And then let's check whether the name change has been successful. So I can click on the name here now. And yes, so we now have new names. We have data point, we have cow, we have milkman, we have feed, and then we have milk yield. Are we all okay up to that point? So it is just a small change that I wanted to make, and I also want to show you that, I mean, we make it more practical. You don't have to fix it. So the next thing that we are going to do now is we are going to draw some GGG plot using the simple command here. So let's see. Okay, so let me zoom. Okay, I'm going to share this. Let me first stop the sharing and then I share the Zoom. Are you seeing my screen? There? Okay, so are you seeing my screen? No. Okay, fine. I just want to. No, I need to. Okay, so we're seeing now. Okay, so this is what we talked about yesterday. So this is our feed E, and then these are the other feeds that we talked about yesterday. The name of the script is the analysis of variance, Makerere, analysis of variance, Makerere. would you send the updated script? No, I'm actually updating the script as you see live in time. So I mean, I'm just going to ask you to update the script. I'm going to rerun. Let me rerun it again so that we can have it. I know there are people who came a bit late. Okay. Okay, so let me just a little bit back. What we have is we started off by installing or installing or downloading these commands, which we are going to use, and then the next thing I told you is to first make sure that you know where your data set is and ensure that the folder which has your data set is the one that you're going to set as your working directory. In mine, I have it on my desktop, and then I have Makerere R training. That is why. So I set mine as set working directory, and that. Please don't run this on your computer because this is for my computer and not for your computer. Okay. So that's the first thing. You need to know where your data is. You need to set that folder where your data is and make it your working directory. So please, can we avoid asking questions that we are not relating to now? If we are running analysis of variance, let's run analysis of variance. The linear, non-linear, we're going to talk about it later. Okay. So after we set the right directory, which a number of you told me the directory was right. The next thing that we did was to go and call our data. Now, this time I use slightly a different command than the one you used previously. So for me, I'm using read.table. Why I'm using read.table is because my data is in a text format. It has an extension txt. So I said, open, this is my folder, my file, and then I say header equals true means read the first line, the first row in my data set should be the header or should be the name of the variables. So after we have done that, we went ahead and then we ran that command, and then we checked that, okay, we have not got any red, so that means our command has been successful. So the next thing that we need to do, therefore, is to look at the names of the variable that we have in our data set. So here we find that we have four columns. We have the first column with the name row. We have the second column with the name column. We have the third column with the name treatment. And then we have the last column with the name yield. And then we went ahead and checked our structure. We click on check the structure. And then here we realize here that it tells us this is a data frame with 25 observations on 4 variables or 4 variables. The first variable is called row. It is an integer. The second variable is called column, is also an integer. The third is called treatment is a character, and the final one is called yield. It is numeric. And then we said, well, if we are going to do analysis of variance or we are going to do any other analysis, the factors that are categorical, things that show for us our design of the experiment, that shows for us our treatment, should be classified as factors so that it will become easier for analysis to take place. So we went ahead and did exactly that. So we went and we converted that into a row into a factor, but also not only that, we also level the factor. Instead of having it as 1, 2, 3, 4, 5, we level it as cow 1, cow 2, cow 3, and so on and so forth. Then we went and did the same thing We did the same thing for the row, we did the same thing for the column, we did the same thing for treatment. So we can now check actually to find out that we'd actually done the conversion. So to check, what we need is we need to run the command, this command here, line 22 based on what I have here. So here, you have the str, and you put in bracket the name of the data frame, that will give you the structure of the data set. So we ran the structure of the data set, and then this time we find that we find now this time we have row is now a factor with 5 levels. We have this cow and all that. Okay, so the next thing that I wanted to do, I wanted to change a little bit my data set. So I want to create another column, which is just going to level my observation from 1 to 25, because this is a Latin square. So that means we have 25 observation. So I'm going to create a new variable called data point, and that observation is just going to be 1 up to 25. So we can run this. Okay, so after running this, you can even check what it is in it. If you click on this, we'll tell you it is 1, 2, 3, 4, 5 up to 25. So I want to combine it to introduce it into my data set. So what I'm going to do in this case is I'm going to create a new Latin square data with this command. cbind means combine using columns. Get what I've just created, put it as the first column, and then the second up to the 5th column will be from my original data set. So I can run this, and then I can check. This, and in this case, we're going to see that we now have 5 variable instead of 4 because we've created just 1. And okay, so that's what we've done so far. The next thing that we are going to do is we are going to change the names of the variables in our data set. I created new names here. So the first column is going to remain the same as data point. The second column is going to become milk cow. The third one will become milkman. The other one will become feed, and then the other one will be feed yield. So that's going to be the new names that we are going to give this. So we can change this. Okay, so let's check whether the names have actually changed now. So we can click on and check the names, and in fact, the names have been changed. So the first column is called data point. The second column is called cow, where you have your cow 1, 1, cow 2, cow 3, cow 4, cow 5. The third column will be the milkman. So you have your milkman 1, 2, 3, 4, 5. Then you have the feed, which is A, B, C, D, up to F. And then you have the milk yield itself. Okay. So the next thing that we are going to do now is we are going to draw our ggplot, which we already drew the first one. And it did show for us that the feed, the first 4, 5 feeds, the first 4 feeds are actually very similar in terms of performance, but the feed E seems to perform differently. And then we can go ahead and then look at the ggplot for the feed, but this time we look at the different cows. So you have cow number 1, cow number 2, cow number 3. I hope you have the graphs. Okay, so you follow your own graph. Unfortunately, you're not sitting near each other, so I cannot tell you to look at what your neighbor has drawn. So you can look at mine. I'm the nearest neighbor to you now. Okay, so we can also draw for the feed, but also look at the different milkmen. So you can see in all cases, maybe let me zoom, and then I stop sharing first, then I share again, the zoom one. Okay, so I seeing my screen? At least my neighbors here can tell me whether they're seeing my screen. I assume if the two ladies have seen my screen, then you're also seeing it. So you can see that in all the different cows, feed E performs very poorly, which is actually okay. But cow number 4, the difference between E and D were actually quite similar in one or the other. But the rest actually the rest are different. Okay. Okay, so we can go on and continue doing so there was also a point plot and so on. So it looks like you have slightly a different script than what but you could also what you can do, you can actually draw this now. You can see now for treatment A, you can have the performance of your different cows. So cow 1, 2, 3, 4. For treatment B, you can have the different cows. For treatment C, for treatment D. So these are some of the flavor that you can actually have with you. The next one, you can run it with feeds and milkman. So you can see that in E, you can see E generally is low. And then you see milkman number 5. In E, milkman number 5 at the worst performance, but then you have all this. So sometimes if you have a lot of data points and you have problem in observing, you can actually use dot plots with different colors, and this can actually help you to make things look beautiful, look beautiful. And you see how actually R can give you very beautiful graphs. We can do the same with the milkman, the box plot for the milkman. Okay, so those are the plots that we saw yesterday. Oh, the plots, the package is not installing. Which particular package is not installing? So if the package not installing, then probably you'll not be able to run some of the things that we are running. But you can probably for now just look at what we are trying to do here, and then later we can sort your problem out, and then we'll be able to progress. Are we okay? We say, which package should I install? The packages are on top of the scripts. The packages are up on top of the script. Okay, so the next one is just, I'm going to just run the normal analysis of variance that we saw the output yesterday. So remember, we started with a null model. With a null model, this is how we fit a null model. We look at milk yield, and then we are fitting it with 1. 1 means the constant that we are fitting it with, and the data is the Latin square. So we can run this. So you can see from here that you don't have, there is no F value, there is no P, the probability is not there, F is not there. That is what we have because we are not testing anything here. Then the next thing that we've done is we are going to run model number 2, which is now we're only looking at a feed. So the first one we had with the 1, the second one now we are going to have it with the feed. And then we can run that. So you see the response is there. The p-value here is the 0.003619, which we say is less than 0.05. So we declare that there is significant difference between these values here. So please, we're not going to run this. We're not going to run this value, or we are not going to run line 44. Don't run this particular line. You can run plot 45. You can run plot 1 model which equals 5. Check this. Just look at this command that I've highlighted. You can start running it from there. You see them one at a time. I'm not actually, for the moment, I'm not very much interested in this. Just let me see what I have here, then we can have a look at this. Okay, let me just expand this, and then we can have a look at. Okay, so here we have our factors here, and then we have our residual, and what we can see that in A, there seems to be a bit lower variability. There's a lot more variability in E, and this one we saw yesterday quite well. So I'm not going to go get bogged down into this. Let me just run this quickly. So you can run each of these. Please, you can run each of these and see what is happening here. You can run 1, you can run 2. So I want you to go and run the box plot. Run the box plot, line 50 of mine. You can run that. I don't want to run all these things in the interest of time. Okay, so this is what we produced yesterday. This is showing us the variability, the high variability in E, and then we have low variability in A and B, and so on and so forth. We talked about this extensively yesterday. And then we can run for model 1 for the cow. And then you can run the point and all that. So that is more or less the checking. And then I drew for you those beautiful histogram with the fit for normal distribution inside here. So I can zoom this a little bit, and then we can have a look at it. Okay, so this is what we looked at, and the command that I just ran is the one that should be able to produce for you this one here. So as long as you ran all the previous steps well, you should not be able to have any problem running the different scripts that we have there with you. So the same observation, that the same thing that we ran for model 1, we can run for model 2, we can run for model 3, we can run for model 4, and so on and so forth. What I want to do now is to try to go and look at the factorial, and then I give opportunity to my colleagues to continue. I requested you to run this model over the night. I don't know how many of you succeeded. Somebody saying error in combined versus that. Okay, so for now, let me first go and look at the second example, and then we can come back and okay. So the factorial one is, with the factorial one, we are just generating the data. I have not saved any data set, so we are generating the data set. So the first thing we are trying to do here is we are starting with generating what we call gender, and here we are looking at female, and there should be 24 female in this study. So we are going to have this command here will provide for us female 24 times, and then the next one here will provide for us female male 24 times, and then we can combine together, so will give us a total of 48 participants that we have. So we can run this. Okay, so let me see what is in the gender here. So you can see what we have done here is we just have female, male. This is what this command has generated for us. This is command here. So this one say replicate female 24 times. So this is what we have here. And this one say replicate male 24 times. And then this one say combine them into one vector. The next thing we are going to do, we're going to create another variable called alcohol. So we say replicate, that mean get this none, replicate it 8 times. Get 2 bottles, replicate it 8 times. Get 4 bottles, replicate it 8 times, and then continue doing the same. So you finish. Remember, this one is supposed to be 24 of them. So here you have 8, there are 24 for the female, and then you create another set, 24 for the male. And then, so we can run that, will give us our alcohol, will give us that. So you can see here, we have none, we have 2 bottles, we have 4 bottles, and so on and so forth. The next one that we're going to do, we are going to now to look at, remember we had the attractiveness here. So these were like for the first is 65, 70, 80, 70, 60, 60. So we can also create that. So we have created now 3 objects. The first, we have this object called attractiveness that measures the percentage of the attractiveness of the photos. And then this one that looks at the alcohol, and then the other one that looks at the gender. And then we can now combine them together into a data frame. But we're using cbind because we're saying put each of them in a column. So the first column is going to have gender. The second column is going to have alcohol. The third column is going to have attractiveness. So once we have combined them into columns here, then the next command will come and make them a data frame. So a data frame would then mean you have a combination of combinations of numerical characters and so on and so forth together. So we can run this command here to give us that. So we can then look at the dimension or what we have created. So we created the dimension here. It is 48 by 3. We can also look at the names. We can just type names in the console, and then we put in attract, which is our attract data, and we tell us the names. They have gender, we have alcohol, we have attractiveness, and then we can also look at the structure of this set, which will tell us that this is a data frame with 48 observations of 3 variables. Gender is character. Alcohol is also character. And then it also tells us that even the attractiveness is actually character. So we need to convert them into the right format. So the first thing we are doing here is we can convert gender into factor. We have seen how this works before. We also need to convert alcohol into a factor. And then we run together. What's the difference between residual and studentized residual? The difference is here is one is standardized. In standardized means the values are made to be within a certain range. Okay, so let me first get this and then we can answer some of these questions here. So remember, attractiveness is supposed to be percentage, supposed to be number. So it's supposed to be numeric, but in our case, it was actually structure. So we need to change this and make it numeric. So now, after we have done all these things, we need to check the fruit of our work, and we check the structure and ensure that things have changed. So we can look at that. Okay, so you can see gender is now factor at 2 levels, male and female. Alcohol is factor at 3 levels, none, 2 bottles and 4 bottles. And then attractiveness now is actually a numeric now. So that means we can get the mean, we can get the what of that. Okay. So from that now, we can go ahead and calculate and do our ggplot. So I've squeezed my margin here too much. So I need to okay. So as we saw yesterday, from here you can see there is none. Maybe let me zoom this. I stop sharing and then I can first zoom. Then I can go back to sharing and then okay. So you can see from here that none, 2 bottles are similar, but then 4 bottles as a lower median. So that was what we saw yesterday. And so we can go and look at the attractiveness by gender. So we can see that both male and female seems to have similar attractiveness, viewing of attractiveness or choice, irrespective of whether they have taken alcohol or not, but there seems to be a lot more variation within the male compared to the female. And then we can look at a combination of both alcohol and gender together and see what that implies. So here you can see here, let me zoom. I can stop the sharing and share again. Okay, so as I indicated yesterday, so you can see from here that with the female, it looks like whether they take alcohol or not, their choice of a choice of mate seems to be unaffected. But for the male, if the males have not taken or taken 2 bottles, they actually choose a more attractive mate, and they even seems to perform better than the women. But immediately they take 4 bottles of beer, then you see the whole thing goes completely off. So this is the point of no return now. So you want back, so you can see how to sort yourself out. Okay. So we can then look at yesterday we generated a few summary statistics, and this was just a simple command by attractiveness, by a different category. So we saw this yesterday. It's just a simple mean and a 5-figure summary, and then you have that. So you can see from there how we can generate all these things. Yeah, okay, let me see. Okay, so then what I showed you yesterday, we had the model, analysis of variance. We had a model for each of them. So we first had the model for gender alone. So from here, we can see that gender, the p-value is greater than 0.05. So there's no difference between the gender as we actually saw in our summary. And then we can also plot the effect. So you can see from here, the female seems to have a higher mean compared to the male, but when you bring in the confidence interval, there is actually no difference between male and female as far as choice is concerned if you ignore the effect of the alcohol. We can also fit the second model. This time now, the model looks at alcohol, ignoring male and female. So here you have the p-value is less than 0.05. So there is a significant effect of alcohol if you ignore gender. We can plot that. So it'll give us, so you can see from here, I can zoom this a bit. Car. The package is called car. Okay, so you can see from here that none and 2 bottles of beer, which seems to be at the same level, but 4 bottles of beer certainly diminishes the choices. After 4 bottles of beer, you cannot differentiate between people of opposite sex. So the point, take-home point is leave the bar early when you are still sober. Noted. But yeah, and you don't drink, so you have no problem. You can stay late in the bar. So if you drink, you leave the bar early. Okay, so we saw that, okay, gender was not significant, alcohol was significant, and then the interaction between alcohol and gender was also significant. And then we plotted we plotted this, and then I think after this, I can share, so I can assure my colleague Ellen, that she doesn't need to, for the female, she doesn't need to worry about drinking and making the wrong choice. But for the men, certainly there will be a difference between those who take beer and those who take beer as far as that is concerned. And what I'm trying to present here is not, none of you is going to study about people taking alcohol in a bar. What this is just to illustrate the point as quickly and as clearly as possible. And from this, you should be able to apply this to your different studies. Okay. Then the next few lines that, of course, then we had the issue of the contrast. We looked at how to define the contrast. Maybe I spend a few more minutes here. So the thing here is then that if you want to contrast alcohol, so there are three types, three levels in alcohol. There was the none, there is 1, 2 bottles, and then there are 4 bottles. So that means the degrees of freedom in the analysis of variance table for alcohol is going to be 2. And that means I can get at most 2 pieces of information that are independent of each other, and those are what called orthogonal contrast. So with orthogonal contrast here, we can compare no alcohol versus some alcohol, which is either 2 bottles or 4 bottles. So this is the first one. And I told you this is none versus some alcohol. So as you can see here, these values here add to 0. And then here, after we have tested none versus some alcohol, we realize that, okay, there is actually a difference between none and some alcohol. Now let's go and look at the alcohol now. We compare 2 versus none. So versus 4, rather, sorry. 2 versus 4. And then for gender, we have only 2 gender, so 1 degrees of freedom. That means we can only have 1 contrast in gender, which is orthogonal. So here you have male versus female. So what we can do then, we create the contrast first. After creating the contrast, we can check that contrast here. So you tell us here that the contrast here is none, 2, and then some, which is 1, 1. And then here you have -1, -2. You can also check the contrast in gender, and then you have your -1, +1. It doesn't matter which of these has -1, which one has +1. As long as one is positive, one is negative, you're good to go. So we now can come and run. Remember now we are running actually the same model. But in this case now, our data set has a modification because the contrast is already attached to the data set. So we can run this. Okay, so this is where we try to push this one a bit up. Okay, so here then we have our gender, which is male versus female, and from here it's not significant. So there's no difference between male and female. And then here, when we come to alcohol 1, which is some alcohol versus none, there is a significant difference. So we say, okay, since there's significant difference between some alcohol versus none, let's go and check the alcohol themselves, alcohol now, compare them. So we come here with alcohol 2, we are comparing 2 versus 4, which is actually significant. Now, the next thing that we're going to look at is we're looking at this. This is now the interaction now. We're going to look at these 2 interacting with gender. So we have here gender 1, alcohol 1. Remember, alcohol 1, there was significant difference between some versus none. So the question is, does that difference between some versus none, does that difference depends on gender? The question is yes. And as I just said, if you are a female, you're not going to be affected by alcohol as far as the choice of your mate is concerned. But if you're male, then you have to be careful about how much you take if you're planning to get a lifetime. Okay, then we have gender and alcohol 2. So the alkyl 2 was telling us was looking at 2 bottles of beer versus 4 bottles of beer, and we found it significant. And then we also found out that actually will depends on whether you're male or female. If you're female, you don't need to worry whether you've taken 2 or taken 4. Your choice will remain more or less similar. If you've taken, but that choice is only as far as attraction is concerned. In terms of the morality of the person, probably since you're all in the bar, we assume you're all at the same level. Okay. So that is the our simple model for that is for the contrast. Then we went ahead to look at the simple effect. So we look at the simple effect as cutting across, like we say, if we fix level of this factor, what happens to the when we compare the level of the other factor, what's happened? So that's where we had to create we created different factors, and then so there is a simple command here called GL, which actually generates a factor with n equals 6 levels, and then k equals 8. That's the number of replications. So what you have 6 times 8, which is actually giving us your 48. And then here we're creating factor for simple effect. And we are saying simple effect, we have also 6 level, and then we level as female none, female 2 bottles, female 4 bottles, then become male none, male 2 bottles, and so what this one does is just a simple thing that you need to take a look at. And then if we look, let's see what we have produced here. So if this is the first 6 observations, so you can see from here, I have female, the gender is female, alcohol is none, and then this is the attractiveness. The simple effect that we can test for is female none, female none, female none. So, and then from here you go to female 2, female 3, and so on and so forth. So then we still come back and create our contrast. So remember alcohol 1 effect. So we are comparing none versus some. So none for female and none for male, they both have negative sign. And then we have this sum for female and sum for male. So here the total is still going to give us, the sum is going to give us 0. And then here alcohol, alcohol 2, mean we are looking at 2 bottles versus 4. So there's 2 for female, 2 for male, 1 for female, and 1 for male. So you can see negative, negative, positive, positive, and then give us that. Then gender, we are looking at gender none, we're looking at female none and male none. Gender 2 bottles, so you can look at female 2 bottles, male 2 bottles, and then gender 4, that is female 2 bottles, 4 bottles, and then male 4 bottles. Okay, I'm going to okay, let's first run this, then I go back a little bit to the contrast, and then we can, this is also contrast. Okay, so here then we have the different contrasts that we've created. We can just run them. Okay, so then we combine them together into one particular object, which is called simple. And then we are going to say, okay, get our data set here. Remember, we created something called simple effect and attach that contrast to the simple effect. We run there, we run our model, and then there we go. Let me just look at this, and then we Okay. Okay, so here we have our simple effect. Simple effect alcohol 1 is significant. Simple effect alcohol 2 is significant. Simple effect gender, none is not significant. Simple effect gender 2 bottle is not significant. And simple effect gender 4 bottle is significant. So that is so you see that by the time you reach this stage, you need to be able to actually have a good understanding of what you're trying to compare. And this is where I said, in contrast, you need to have a good structure in your data so that you're able to actually make comparisons that are very meaningful. Excuse. So in this case, for example, if you look at the different contrasts, the different gender, you see now that it kind of makes a lot of sense to make those kind of comparison. And those comparisons cannot be made by simply having pairwise comparison, because pairwise comparison may not actually be that useful. Okay, so let me try to re-explain let me try to re-explain the contrast. Maybe I can open a blank, and this will be the last point, and then I'm going to ask my colleagues to take over. So let me reshare this, my PowerPoint. Okay, so here the idea of a contrast here is that, okay, remember here we have none. We have none. We have 2 bottles, and we have 4 bottles. Okay, so the issue here is now we want to compare none versus some alcohol, And remember, in the different categories, okay, so here we are comparing group, we are comparing 1 versus 2. So it's not just comparing 2 and none and 2 bottles, none and 4 bottles. That's not the comparison we want. We want to say, okay, if I take some alcohol versus if somebody doesn't take, does it affect our change? Does it affect the score? So what happens here is then that, okay, we can actually start from our null hypothesis here. The null hypothesis will tell us that that the mean of none is actually equals to the average of the 2 of mu 2 plus mu 4. So that is what that whole thing is about. Of course, we can get rid of, there are many people who don't like fractions, so we can get rid of fraction by multiplying both sides by 2. So if I multiply this by 2, I multiply this side also by 2, then this will cancel with this and that. So, and then I will have 2 mu n should then be equal to mu 2 plus mu 4. Okay. So I can bring them two together. If this side is the same as that side, so I can then say 2 mu n minus mu 2 minus mu 4 should be equal to 0. That is what I have here. Okay. So which actually would mean that in terms of the coefficient, of course, you can assume mathematically, we can assume that there's a 1 here and there's a 1 there. Okay. So here then you have your 2 as the coefficient for this side, and then -1, and then -1 as the coefficient of the other side. So what we've actually done, then we need to tell R that this is the coefficient that we want. This is our contrast. And once we have this contrast, then so at the end of the day, this contrast then will come and test whether a none versus some is significantly different. So if none versus some, so in this case, actually after testing, we found out that it is actually significantly different. So the next thing then we can go and test the next contrast. The next contrast now is not going to be interested in this one anymore. So this becomes a 0. Then we are testing this versus that. That's why one of them becomes negative. So if that is also significant, then the next thing that we need to do is then we need actually then to test for the interaction with gender. If it is gender 1 or gender 2, what will certainly happen. Okay. So I think this is more or less what I can do for now. I think we still have a few things that my colleagues would have to cover. So I don't want to do that. How do we deal with the missing value, especially if we say one male slips up and we don't get the attractiveness value? That is interesting. There are different ways of dealing with the missing values. You could actually estimate using there are many ways of imputing missing values, but there are also things like mixed model that can actually handle missing value in a different way, but that can be discussed in another way. So for now, I think I will say thank you, and then I will pass you over to Madame Susan. Okay, thank you very much. Just hold on a little bit. I stop sharing and I switch off my microphone.
Good morning, participants. I had said that in case we have time, we can run the model building. It's going to be a short practical on model building. So let me load the PowerPoint and then we go into practicals. For us. Huh? Model building. Okay. Oh, I'd forgotten to open it in a good way. So we have to do open with. Let me even open R so that
certificate issue. Keep in touch, we'll discuss.
We were not told whether they can get certificates. Okay, let me share the screen. We want to use the remaining time between now and midday to finish model building. So I'm going to leave some of the slides for you to read. It's not very difficult. I'm just going to explain the concept of model building and the criteria. Those participants raising up their hands, please write your questions in the chat or the Q&A. The option for selecting you has been muted, so we cannot really select you when you raise your hands. Okay, model building. When we have so many regressors, we've collected a lot of data. There are so many independent variables. We would like to select which independent variables explain the variability in the response. So sometimes it is difficult to fit like 15 independent variables onto the response. So in that case, we use a method called variable selection, which helps us to select a subset of the regressors that explain a lot of variation in the response. Now, there are three methods of selecting subsets of regressors necessary in the model. Why do we do model building? We would like to end up with a simple model, which is cheap, because the more variables you have in a model, the more expensive it becomes when it comes to data collection. So remember that when you formulate a model, we do prediction with that model, or somebody can pick up that model and use it to analyze their own data. But if the model has so many variables, that means that particular person using your model is going to incur more costs in collecting the variables. So we need a simple model. It is easier to interpret and also cheap to collect data. So if we have this regression equation where growth is our response and growth is a function of rainfall, soil type, variety, and sunlight plus fertilizer, then that model can be represented statistically as Y representing growth, beta naught is the intercept, beta 1 is the slope for rainfall, beta 2 is the slope for soil type, etc. up to beta 6. So we can use the variable selection method to actually remove some of these variables, which may not be necessary in explaining the variability in growth. So these variable selection methods include stepwise, forward selection, and backward elimination. So in all these methods, one independent variable is either added at a time or deleted, depending on the F statistics or the p-value. Okay. So I've just said that in the stepwise selection method, we have forward selection, backward selection, and then stepwise selection. And then in R, there's also two extra methods called all subsets and best subset as other methods of selecting variables, as we shall see in practical. Now, forward selection. In forward selection, we begin with a model with the intercept only. No variables, no independent variables added. Now, the criteria we use is that we set our alpha. Here, alpha, we've set it as 0.05. That is the significance level the researcher chooses to use in testing the hypothesis. Now, the regressors are inserted in the model one at a time, depending on whether the corresponding p-value for those regressors is less than 0.05. The first regressor selected under forward selection to be added in the model is one with the largest correlation with the response. So the first regressor is one with the highest correlation with the response. It's added in the model, and then the program checks whether the p-value is less than 0.05, and then that particular regressor is left in the model. The regressor is the independent variable. So the process continues. The second regressor also added is one with the highest correlation among the ones that are left, the independent variables with a response. So it is also added in the model, but it is adjusted for the effect of the first one. So we've added independent variable 1 to the model with the intercept. Then assessed. If it is significant, is left in the model. Then x2 is added in the model. Now x2 is adjusted for the effect of x1 being the model, and also for it being added in the model. So if x2, once added in the model, remains significant, even in the presence of x1, then it is left in the model. So the process continues like that until the final step where the last added independent variable or regressor is significant, given that there are other independent variables in the model. So that is forward selection. Backward selection is the opposite of forward selection. In backward selection, we start with a model with all the regressors. So if you have 6 variables, they are all put in the model, then one by one is dropped out, depending on the alpha criteria. So if we find that regressor x6 is non-significant, it is dropped out of the model. So the process continues like that until the final model has only regressors whose p-values are less than 0.05. So that is the backward selection. Then stepwise selection combines both forward and backward selection. That is a stepwise selection. So it starts as forward selection with a model with no intercept, with no regressor. It has only intercept, then adds in x1. If x1 is significant, is left to stay in the what? In the model. Then x2 is brought. As x2 is brought in the model, x1 is being assessed for being dropped out of the model. Okay, because it's combining both forward and backward. So a variable is entered because its p-value is less than 0.05. Then we bring in x2. x2 is being entered because the p-value is less than 0.05, but x1 is being assessed to be removed in the case its p-value now increases more than 0.05. So if we add x2 and x1's p-value becomes greater than 0.05, it is removed out of the model. So the process continues like that until we get a final model where all the independent variables are significant at both alpha to enter and alpha to remove. Okay, so how do we now evaluate the best or the most appropriate regression model? Because each method may end up giving a different model. So how do we assess? We have some criteria. We have the first one is called R-squared adjust. We looked at this when we were looking at multiple regression. R-squared adjust tells us the proportion of variability explained in the response by the model. So for us to choose among 3 models which we have, then if any of the model has the highest R-squared adjust, then that is the best model. We also use mean square error. Mean square error is the one we use to test whether the regression mean square is significant, whether the amount of variability explained by regression is significant. So mean square error, if it is small, then that model is good. Remember that when we are fitting a model, we are minimizing the difference between the fitted line and the observed values. So if the difference is small, then that model is good. So this mean square is measuring that difference between the observed and the fitted value. Then AIC is a Akaike information criteria. It also, if it is small, then it is the best model. It tests the difference between a model with intercept and a model with variables added in. So the smaller the AIC value, the better the model. Then we have MAL-CP. MAL-CP denotes the number of parameters in the model. So for a model to be good, the number of parameters has to be equal to, the number of parameters in the model has to be equal to the MAL-CP value. So if you have a model whose number of parameters is equal to MAL-CP, then that model is good. For example, if we have a model with 4 variables, then its CP is going to be 5. Because when you have 4 variables in a model, plus the intercept, you get 5 parameters. So the CP should also be equal to 5. Okay. The other criteria we can use is predicted sums of squares. This is the ability of the model to predict the response. So if we have a smaller value, that means that the predicted values of Y are almost close to the observed values, meaning that model predicts well the observed values. So that is the PRESS, the predicted sums of squares. Okay. Any questions so far? I have been talking. Let me see in the chat. Any question? You seem to be understanding everything. Okay, great. Great. If we are understanding, then we go ahead and then do practicals. We are going to do a very simple practical, and it's going to be very interesting. Okay, so we can use those criteria to choose among the different models. Okay. So the next slide just tells us, why don't we use R-squared instead of, and we use R-squared adjust. We mentioned when we were talking about multiple regression that R-squared, when we add in regressors, it is inflated. It keeps on increasing, increasing. But R-squared adjust does not increase as more regressors are added in the model. That's why it is preferred. Actually, it adjusts for any regressor added in the model. It keeps adjusting the number of parameters being added in the model. That's why we prefer using R-squared adjust instead of R-squared. So in this case, the higher the value of R-squared adjust, the better the model. Okay, so we are almost done with the, after selecting the best model, you go again and test the regression assumptions to see whether they are valid. You remember the assumptions. We assume the response is linearly related to the independent variables. We assume the unexplained error or variation or residual is normally distributed with mean 0 and constant variance. The unexplained random errors are independent. And also we assume the independent variables are not correlated. So you check for those assumptions And once you don't violate any of them, then your model is now good to be used for prediction and also for other programming purposes. Okay. So let's move to R. Hopefully there's no question. So we are going to R. I'm going to stop sharing this and then we share R. Should we use all these criteria at the same time? Yes. The model which fulfills all those criteria is the one that you choose, as we are going to see in the practical. Okay, so let me go to R. I'm going to share my R script. It's called model building. So you also go and open model building so that we can go through the practical. It is like a short practical. And I hope that, pardon? What do I recap? The different steps. Or the criteria for validating. Okay, we said that once you can, when you run your analysis of variable selection, you might find that you're getting different models for the same data, but you want to select among those models, which one is the best. So we said we can use R squared adjust and look at all the models, assuming you have 3 models. So the one with the highest R squared adjust is the one you choose. Now look at the mean square error, the one with a small mean square error. In addition to having a high R squared adjust, that model should have a small mean square. Then when we look at CP, that model should have the number of parameters in the model should at least approximately be equal to the CP value. And also press. The one with a small press should be the best model because press is the ability of the model to do prediction. So that's how we use those criteria. So let's go to the practical and we see how we apply criteria to the data set. So I am assuming that everybody has opened model building final. Why do I call it final? And what is the difference between step to validate the model? Huh? What is the difference? The different step to validate the model. Oh, okay. Okay, so in the chat, I would like to know whether you've opened the script and please load the different packages. And in case you had not loaded OLSRR, please install it first and then you load. The data set we are going to use is under the package called Far Away. So install that package. You can see, let me zoom in so that I'm going to zoom in so that the words are a little bit bigger. Okay, so you can see that there is this package called Far Away. That's where I got the data set, which I'm using now. So please make sure I install. I'm giving you 2 minutes. Install this package called Far Away. It uses only 1 minute to install and then also load it. So what I'm going to do, I'm going to load these packages as you sort yourself. So I load all these ones. And I also load Far Away. So you can imagine, it's going to say warning message package Far Away was built under the version 4.1.3. That is not a problem. It has been loaded, only that they are telling you that you have a higher version and it was made in the other lower version, but still it's going to work. Okay, so in the chat, is everybody good to go? Let's see in the chat. Please zoom in, Prof. Okay. I'm going to zoom in. There we go. Okay. So in the chat, should I start? Because I want us to start and move on. Oh, no, I got this problem. Attaching package, the following. Oh, no, that is okay. You go on. There's no problem. There's no problem there. Okay, should I continue? Okay, thank you. I'm going to continue. I'm going to run line 16. We are calling that data set. It's called state. This data set consists of life expectancy. It has variables like the population. It has variables like frost. It has, as we shall see, some of the variables have run out of my head. So let's call this data set called state. So run line 16. When you run it, and then we are running the second line 17, we are formulating a data frame, and our object is called state data. And we are saying read the row names the way they appear. So there we are. And the next line 18 is going to show us the data. So I'm just going to go up here and see our data. So if you scroll in the console, we shall see we have population, income, illiteracy, life expectancy, murder, and high school graduate. So they are asking, what factors affect life expectancy? Is it murder? Is it illiteracy? Is it income, population, and high school graduate? So we want to know the factors which influence life expectancy. Is life expectancy affected by literacy, income? Let's see. So remember that when we are doing data analysis, we do our exploratory data analysis. So here I'm just doing a simple one, the summary. Okay. So summary gives you the mean, median, mode for all this. I think let's not go into the interpretation of these means and median. I want us to go straight into what we want to learn because of time. Oh, okay, here we don't need really to set the directorate because we are getting our data from the saved package called the faraway. Huh? We don't need to set the directorate, okay? So just run the code and they will work. If the data set was saved in a folder, then we can do that. So for example, we can write state data in a folder and write it in R, and next time you want to use it, you call it back. If you don't want to install far away or load it, okay? Okay, so we are going to run line 21. Line 21 is a regression. We are calling the object of line 21 G, and we are using the general linear. LM is general linear model. Life expectancy is our response, and it is a function of all the variables. Dot, comma, tells R that you run all the variables instead of writing all of them in a statement. The data set is called state data. So please run that. And you don't see anything. So you say summarize G, which is our object, and you will see something. So let's see what is happening in the console. So you see it is given us the coefficients. I hope we are all together. We have the coefficients. We have the intercept, which is the value of life expectancy when all these variables are equal to 0. We can see life expectancy increases by 5.1 if population increases by 1. Then life expectancy decreases by 2.1 when income increases by 1 unit. I'm interpreting the coefficients, the estimates. Then life expectancy increases by 3.38 when we increase illiteracy by 1 unit, maybe by 1 year. Then life expectancy decreases when 1 person is murdered. I'm assuming that the murder is number of people being murdered. So if 1 person is murdered, life expectancy decreases by 3.01. When we go to high school graduate, life expectancy increases by 4.89 if somebody has got high school graduation. Okay, life expectancy decreases when frost is when we have snow and it is very chilly. If it increases by 1 unit, then life expectancy decreases by 5.74. Area, and then here tells us life expectancy decreases by 7.38 if area increases by 1 square unit. Okay. And then R squared adjust for this analysis is 0.6922, which is 69% of the variability has been explained in life expectancy by the regression model. And overall, there is a significant linear relationship between life expectancy and all those parameters. Using this p-value of 2.53, 4 times 10 to the power minus 10, it is smaller than 0.05. That's why we conclude that overall, there is a significant linear relationship between life expectancy and all these variables. Okay, but that is just the regression, the general multiple regression. Now let's do model building. Model building, we are first of all going to do forward selection. And the code we are going to use is code 26. It says forward is equal to OLS underscore step underscore forward underscore p-value, and G is our model. P, this is p-value to enter is equal to 0.05. Okay, let's run that line, and then we run the forward. So let's look at the console. And I'm going to increase this, make it bigger. You can do the same, widen your console so that you're able to see the output. It has given us a selection summary of the forward selection without the steps. So in the next step, we can ask for the details so that we see how the variables were eliminated and why. So here, it has given us an overall model. In the overall model, it entered murder, entered high school graduate, and frost. That is in the overall model. And it's telling us that the AIC after entering model, if you look at AIC, is 129.2 when murder was entered, CP is 16, and R squared adjust is 60%. So when we have only murder, only one variable called murder in the model, our R squared adjust is 60%, AIC is 129.3. When we include high school graduates, our R squared adjust is 64.85%. Our CP is 9, and AIC is 123. Then the residual mean square is 0.975. Remember, small is good for residual mean square, and AIC small is good. So when they enter frost in the last section, we find that our R squared adjust has improved by some degree of 0.05. Then CP has reduced to 3.7. Remember, we have 3 variables. Therefore, our CP is going to be 4. The intercept plus the 3 parameters, the 3 slopes. So if CP is 3.7, then that is a good model. And SAIC has reduced compared to when we have MADA and high school graduate in the model alone without frost. And also the residual mean square has decreased. So tentatively, we can select that the model with 3 variables, MADA, high school graduate, and frost is a good model. Let's look at the details briefly. So when we go to line 30, we are asking the program to give us all the details. So just run line 30 and it gives you a lot of information. So let's just look at that very briefly. And I make this wider so that we can. So you go up to the beginning where the analysis starts from. So scroll up in your console, and there is where there's forward selection method, candidate terms. So those are the independent variables that you're entering. And step 0, this is forward selection. We start with the intercept. That's why you see it is saying life is intercept. The AIC for that model is 174.32. Okay. Now, the AIC decreases from 174.3 to 129.28. Let's go on. I'm just going to use AIC and then we'll look at the final model because of time. Then high school graduate, when it is added in the model, the AIC decreases from 129.3 to 123.96. Then when we add frost, the AIC decreases from 123 to 117.9. But if you look also other criteria, R squared adjust is also improving. Then we add in population, and the AIC has decreased from 117.9 to 115.7. So then it says no more variables added. Okay, so our final model is life expectancy is a function of MADA, high school graduate, frost, and population density. And in the table below, it is showing you the variables which were removed. It removed the income, illiteracy, and area. And then in the final output, it gives you the final R squared mean square error is 0.85 for the final model. R squared adjust is 0.71. Then the predicted R squared is 66. Then if we look at the ANOVA for the overall model, the p-value is 0.00, which is significant. It also gives you the parameter estimates for MADA, high school graduate, frost, and population, and the corresponding t-value, p-value. So you can see that all these variables are significant at 5%. Then it goes on to give you the AIC. As you add one parameter in the model, how does the AIC behave? So it is telling you AIC is decreasing and R squared adjust is increasing. The RAS is the residual sums of squares. It is also decreasing. So that is it for forward selection, unless if there is a question in the chat. Should I go to backward elimination in the chat? Oh, population is equal to 0.00. It has been rounded off to 3 decimal places, but if we ask for more decimal places, it should be more than 0, 0. Okay, so everybody is saying we go on. So backward elimination, you can see that it is the same code, only that instead of forward, we replace with the backward. And instead of pre-enter, we put pre-remove. That is probability to remove. So let's run that line and also that one. And I'm going to run also 39 and 40. So we get the details at a go. So I've run 39 and 40, and I want us to go to the details. So scroll until backward. Okay, so let's look at the details one, the detailed version of backward, because it has everything with the p-values. So first of all, it shows you the candidates you're entering in the model. We said backward starts with the model with everything entered. So with all the regressors, you can see that when all regressors are added in the model, the AIC value is 121.7. Okay. R squared adjust. If you look at our R squared adjust, when you enter area, it is 69%. When you enter income, it is 69 still. When you enter literacy, it is 69%. When you enter population, it goes to 67.7%. Like that, when you enter murder, it keeps on decreasing. Okay, so let's see. R squared that just removes those variables which are non-significant. So it has found that area is non-significant and area has been removed. When area is removed, the AIC reduces to 119 from 129. So let's go to the next step. We remove illiteracy. When illiteracy is removed, AIC reduces to 117. And R squared adjust is improving. Also, even other parts are also improving. Then when we remove income, AIC reduces to 115. So now we have a model with population, murder, high school graduate, and first. Then the program says no more variables to remove. So meaning that the variables in the model are all significant. So it shows you the variables removed, area, illiteracy, and income. It gives us a final model showing us our R squared adjust, which is 0.713, shows us the mean square, which is 0.518. And then we go to the overall ANOVA, which is 0.00, the p-value is 0.00, meaning overall, there is a significant linear relationship between life expectancy and all those variables in the model. Then it gives you the parameter estimates and the corresponding p-values. And you can see that we've gotten the same model as in the forward selection. This is a rare case, but you find that in most cases you have this different model. Then it gives you a comparison. It says backward elimination summary. When they had a full model, the AIC was 121.709. R squared adjust is 69.2. Residual was 23.27. When area was removed, AIC reduced to 119.7. When literacy was removed, the AIC reduced to 117.7. When income was removed, AIC reduced to 115.7, and R squared adjust improved to 71.3%. Then our residual sums of squares also reduced to 23.308. So indicating that the best model is the model without all these three variables in. That is backward elimination. Okay, so now I'm going to go to forward stepwise. It includes both backward and forward selection. That is line 44. You can see instead of backward, we have replaced with both forward and forward selection. So, and remember, we are using the same object key, the model we had before. Okay, so here we run this and also run line 48, and so that we have the detailed version. So let's look at the detailed. We are left with only 2 steps to finish. And excuse me a bit, I'm going to remove that so that I run the console without a lot of information in it. Okay. Then I run that so that my console is not overcrowded. Okay, so let's look at stepwise with all things in the model. And we are going to look at the detailed one. So it lists the candidates, those are the regressors. Remember, stepwise starts as a forward selection method, then it includes in backward. So you can see in stepwise, it shows that when life expectant is regressed onto the intercept only, the AIC is 174. Then variables entered stroke removed. That is the second step. So it says, when we enter murder, the AIC reduces to 129.2. So murder is entered. And then it shows us the output for when murder is in the model. And it says when we enter high school graduate, the AIC reduces to 123.968. That is step 2. Step 2, we have murder and high school. So it is also, murder has been tested for entering and being removed. Then they've tested high school for entering. And it has successfully entered because the AIC has reduced. Then we go on and they enter Frost. When Frost is entered, AIC reduces to 117. That is in step 3. So in step 3, they assess murder for being removed, high school graduate for being removed, and Frost for entering the model. Okay, so here in the summary, they are showing you that when Frost enters, AIC is 123.9. When high school graduate is entered, AIC is that, like that. So then it enters population. AIC reduces to 115.733. So step 4 shows you that once all these variables are entered, our final AIC is 115.73. Okay. And it says that if you remove the existing variables that you've entered, then your AIC goes high. You can see the last part, murder, has 159.4. So, and it says that these variables, income, illiteracy, and area, are the ones that were removed. And on that point, it says that no more variables are added or removed from the model. So our final model is a model with the murder, high school graduate, Frost, and population. Okay, so here we are getting the same model, so we have no problem actually selecting among the different models. Okay, so the last part is R gives you, I'm going to delete this. And in case you have a query, my colleagues will help you to answer. There are two methods that R introduces. It introduces a method called all possible subsets, and another method is called best subset. So we are going to run all possible subset. So what does all possible subset? It gives you all possible models for that, for all the independent variables. So it starts with a model with one independent variable, two independent, three, for all the models summarized in all possible. So you're able to know which one actually should have been selected. So that's line 52. Let's run line 52 and we click all. Now it's going to give you a large output. So we combine all in a data frame so it is easy for you to interpret. So next line 56, let's combine information in all in a data frame. And we see how to interpret it. So I'm going to look at the console. You can see it's giving you everything right from number 1 to I don't know which number. Okay, so it is saying that number, that is the model, predictor, R squared adjust, and it has all of them up to AIC, everything is included. But you will see they are below here because it has steps up to 69. So you can see here we have CP on, we have AIC, BIC, and all those included. So this one, if you sit and look, you can look at, if I have murder only in the model, regressed on to life expectancy, the R squared adjust is 60%. When I have literacy only in the model, R squared adjust is 33%. When I have high school graduate only, it is 32.5. When it's income, it is actually 0.09%. So you can see that actually these variables which were removed were not actually really explaining any significant amount of variability in Y. You can see income is 0.09, which is 9%, 9.7%. Frost is 4.7%. Area is 0.9%. Population is showing that when population is alone, then it only explains 10%. No, 1.6%. Then it comes to the two model. When you have murder and high school graduate, the R squared adjust is 64%, 64.8%. So you go on like that and keep on looking at all the criteria, and you can select out which one you want. So if you go to 3, the model with 3 variables, murder, high school, and frost, the R squared adjust is 69.3%. You can compare all these ones. You can put them in a table, a clear table, 3 model, 2 model, and compare in your manuscript as you go on discussing, and look at also the CP, the AIC, and select which model actually is the best model. But we've seen that the model with the 4 variables is the one which is giving us the best model. So that is the all possible. It is such a lengthy thing, but it gives you a detailed insight in every variable that you are assessing. So I'm going to delete this and then run the final part, which is all best subset. Let's run line 63 and 64, and I will look at the questions if there is any. Okay. So line 64 gives us the best subset. Okay, so I'm trying to expand this so that we can visibly see the results. So in the best subset, it only brings out what it considers best as far as the program is concerned. So it is showing you only those predictors which were added in the model. And it is saying that it had 7 options which were the best. A model with only murder alone, a model with murder and high school graduate, a model with murder, high school graduate and frost, a model with population, murder, high school graduate. And now you can compare among these 7 models and you select out the best. So let's go to the detail, the summary. Here is the summary. Let me reduce a bit, zoom out. Okay. I hope it's not too small because I wanted us to have all of them summarized. Just 1 minute. Okay, so let's look at this model. The first model was with murder alone. It gives you the R squared, which is 60.7. R squared adjust is 60%. The CP is 16. Remember, we said CP has to be equal to the number of parameters. And if the model has only one independent variable, its CP should be at least 2. So the CP is 16, meaning it's not really a good model. AIC is 129. Then BIC should also be small, is better. There is mean square for prediction, MSEP, 35, and the rest. So then let's look at model 2. Model 2 has a murder and a high school graduate. Murder and high school graduate. R squared adjust has increased to 64. CP is 9, it has reduced, that is good. AIC has reduced. BIC has reduced. And the rest has also improved. Then we look at model 3. It is also improving. The R squared has improved. Then CP has reduced 3.7. And AIC is 17.9. Even BIC is reducing further. So if we compare all these models, from what you've seen, which one would be the best model? From the criteria we see, let me see in the chart. Which one would you select to be the best model using the values you are seeing in the summary? Using R squared adjust CP, AIC, and BIC. Okay, let me look in the chat. Okay, people are saying model 4, model 4. Okay, we will look at model 4. Everybody is saying model 4, that is good. I don't know because I need also to compare them. Model 4, okay. Everybody is saying model 4. So let's see what is in model 4. Model 4 has population, murder, high school graduate, and frost. So let's look at the details of model 4. Model 4 has R squared adjust of 71%, CP of 2, which is good. AIC has tremendously reduced. Actually, it has the least AIC among all. It has the least CP among all. It has the highest R squared adjust. And, oh, I think you guys are even ahead of me. I hadn't seen that model 4 was the best, but you're doing a good job. I can see that you've understood how to do model building. Now, AIC ends, model 4 ends up to be the best model. So what you do next, we can make this smaller. What we do, the last thing you do after selecting your model, you run the model afresh, then run your residual. you run the model and then run the residual plots as we did and look at the assumptions. And that is it. You're good to go. So I think that one you can do. You can bring back, you can call it maybe P is equal to LM in bracket. Let me go and life expectancy, life.xp. I don't want to write a lot of details, so I'm going to be a lazy one and go and just copy this, control copy. So P is an object. This is the last part we are doing. And so LM is general linear model. This is our response. Instead of a dot, now we are going to say that it is a function of population plus murder plus frost, I think. Oh, high school graduate. High school graduate. Oh, it's not bringing high school graduate. Okay, hold on a bit. Okay, HS dot graduate plus the last one is frost. And then data equals state. So, pardon? HS grad. Okay, there we go. Okay, so let's run that. That is our linear model. And then we do summary in bracket P and run. That's our final model. And we are going to do pow in bracket mfro equals, I don't remember, I hope that is what we said. Stroke 2. Yeah? Okay. Then we do plot. Yes. Okay. Thank you.
I'm sorry, straight away.
Plot. Huh? Plot P. So what we are trying to do is assess the assumptions. So we've run our model, it's called P. And I'm saying I want them arranged in a 2 by 2. Okay, so let's run this. And it says object not found. M4. Do you have an equal sign there? I'm going to go here. Let me get it from here. From regression. There we go. I was making a mistake. Control copy. Okay. We are almost there. No, it is equal to. Okay. Then run. Okay, then we say plot. We could not find plot function. Okay, that is also fine. Okay, yeah, I know why it is saying we could not plot. This is the state data. State data. Okay. Then we do run and could not function.
P, small p.
Small p. So you can see that when you get ready, you don't need to start panicking. It is still saying margin is too large. Okay, we zoom out and zoom out and then zoom out and then run this because the margins were okay. Oh no, it has blotted all of them. Okay, I made a mistake. So this should be P, not that one. Let me run. Okay. And it has only given me one plot. It has given me one plot. Okay, anyway, it has given me a plot here.
Enter. Enter to see the next plot.
Okay, let me.
Enter P.
So the plot given here is residuals versus fitted values, which tests for constant variance. And because this is a random scat of points, and also the red line is almost horizontal, showing that we have constant variance. So then I go to enter. Why is it misbehaving? It has given me the next plot. And it's a normality plot. And you can see most of the points falling on the blue line, indicating that there is normality. Then I click enter to give me the third plot. It takes its time. Oh, I know why it was taking time. In the console, the plot comes automatically, but here, when I hit enter in the RStudio, it takes time. So we have location to also test for constant variance, and you can see that the values, the errors is a random scat of points indicating constant variance. So if we enter, this is the leverage one where it shows that since there are no residuals above the dotted lines, it indicates that we do not have any residual values to worry about. So if any of these dots, the circle are above these dotted lines, which you see starting at 0.5 and then 1, then we would know that we have some residuals which would maybe qualify to be outliers. Okay, so that's really about it. Maybe I want to run this and see whether it's going to work. No, it's not really. Okay, I think that's it. Once you've gotten your final model, you test the assumptions. And remember, when you want to test the assumption of linearity between the response and variables, then you draw the scatter diagrams. Okay. I think that's it, unless if there is a burning question, but I would like to stop here and give you another chance. Click enter while the cursor is in the, okay, thank you so much. Oh, I have to put dv.off before running. You guys are becoming even better than me. Just repeat the interpretation of leverage. I have said that you see the dotted red line, that is the Cook's distance And anything above the Cook's distance or below the Cook's distance shows that that residue is an outlier. And you can go and investigate whether it's a genuine outlier or it is a typo, or then you need to deal with it. Okay, so that is the residuals versus leverage plot. So any of the, if we had all these points and we had some here and then some here, then we would know that a particular residue is an outlier. Okay. Okay, I think I'm ending here, and I thank you so much because you have, I do not have today's script. It is on the Google Drive. You are excellent, and I am proud of teaching you because I've done it so fast. For first time people who have not done model building, it would be so difficult for you to understand, but you picked it so fast, and the questions have been minimal, and I thank you so much for being excellent. Thank you for attending today in large numbers. Me and others, we are so grateful. Please practice. Practice makes perfect. If you keep those scripts and you don't practice, you forget everything. That's all about model building. There's more about regression. Next time, we will, God willing, we will organize another session where we talk about weighted regression, penalized regression, etc. But thank you for being excellent participants. Okay, I hand over to Helen. Oh, I'm told you need a break. I was just doing marathon. So let's have a 5 minutes break since we only have, let's come back at 12:30. Okay, thank you so much. Thank you, you are also excellent. So please go for a break, stretch out, and let's see what Helen gives you. It's also so interesting. So stretch yourself, 12:30, come back. Thank you. Thank you very much. Bye-bye.
Okay, good afternoon. Welcome to the last session for today. I just want to confirm if you can hear me, and then I proceed. Can you hear me? All right. Thank you so much. Good afternoon once again. So in the last hours, we are going to look at, hopefully time will allow, we want to look at analysis of categorical data. If possible, we move on to regression, and then also Poisson regression. But let's see if time will be on our side. So, and analysis of categorical data, remember, since the training started, we've been looking at different levels of data, okay? Different facilitators, Thomas and Susan, have been showing you how you can read different data within R. But sometimes, in case you're collecting data, some variables are categorical in nature. And for you to get the right statistical test to use and also give proper interpretation, you need to understand very well the kind of variables that you are using. So now basically, we are going to go into more details of analyzing categorical data. And here we use what we call the chi-square test, which we use to test for independency. Chi-square test to test for independency between two or more categorical variables. The different examples that you've seen under categorical variables, for example, you can say, if you're talking about gender, it has both a male and a female, and so on. If in case maybe you're talking about different types of cells, you can list them out. All those are categorical in nature, but still depends on the research question that you want to answer. So also you can use the chi-square test to compare multiple observed proportions to multiple expected proportions, as we are going to see. But remember, what we collect or what we get from the data set, those are the observed, but then how do we get the expected frequency or proportions? So to make the work easy, when it comes to categorical values, most of the time it is represented in tabular form, or what you refer to as a cross tabulation, or you can call it a contingency. Okay. All right. So can you hear me now? Somebody saying that no sound. I'm back. Okay, now let's move on. I was still sharing that we can organize the variables in form of a cross tabulation. And this is an example. I mean, in R, we've so far looked at some of these commands, like the command table, in case you want to form a cross tabulation of two categorical variables. In here, what we are looking at the relationship between color and then the price of, it was the price of diamond. But with this representation, I'm only showing you that what we can do in case of cross tabulation, looking at two variables. But by the end of the day, still we need to test and check if one is depending on the other or there is no dependency. And also we shall go ahead and compute the total rows and then the total columns for each respective variable. Okay, Apart from testing the independence of association under the chi-square, it can also be applied in various areas. For example, you can use it to test for equality of proportions in more than two populations. You can use it to test when you're testing the goodness of fit, as well as it measures the extent to which the observed and then the expected frequencies differ. So we are going to look at some of this. We're going to first start with the theory bit, and then later we move on to R and see how it applies. Like I've already mentioned, that categorical data refers to observations that are classified into categories. Whenever you have a variable, but it's classified into categories, what should come at the back of your mind that it is a categorical variable. The numbers are the frequencies, or call them counts. And it is always desirable to know the classification of your data set such that you're able to set the right statistical method that you use and also eases the interpretation of the data. Let's take an example. I'm saying that, for example, in the independence of species, an infection can be interpreted to mean that there is no difference in infection rate between species. That is, the infection rate does not depend on the species. But that is just an hypothesis that we need to prove because there are two of them. So we need to check and see, these two variables, is there any dependency or there isn't? And so since we know that both of them are categorical, then we are going to employ a chi-square test. Let's take this particular example. We are saying that a bunch of 1,500 wooden sticks were divided at random into 3 groups of 500 each. Each group received a different termite repellent treatment, okay? The treated stakes were driven in the group of locations selected at random. 2 years later, the stakes were examined for termites and the data are summarized in the table below. So this is what we are having. We are just taking an example. How will our table look like? And then later we'll shift it into R and see how do you get at a cross-tabulation table or a contingency table. And then from there, how do you derive the chi-square? So here, these are the 2 groups. We're having group 1, group 2, and group 3, all right? And then the other one is we have the other variable for the case of the termite, attacked by a termite and not attacked by the termites, all right? In group 1, we're having 193 in those that were attacked by termites. In group 2, we are having 148. In group 3, we are having 210. And respectively, when you come to those that were not attacked by termites. These subtotals you are seeing at this particular table, it's adding those that were attacked by termites. These are marginal totals. And then also the 949, by summing all that, you come up to that. You're summing the rows, and then when you sum the columns, these are the totals that we are getting for the case of the different groups. Under group 1, the total is 500. Remember, they say they are equal, they are all 500, but they are being distributed. So when you look at this table here, it's what we call a cross-tabulated table or a contingence table. And in this particular case, it is a 2 by 3. We are having 2 columns and then 3. We're having 2 rows and then 3 columns. So it is a 2 by 3 contingency table. One of our group, it has got 3 labels, and then the other group, it has 2 labels. So how do we test for independency in case you're having these 2 variables? Number one, of course, we've been talking about hypothesis testing. And clearly, in one of the presentation, Dr. Thomas was taking us through how do you determine an hypothesis? How do you create a research question such that at the end of the day, you are able to arrive to the conclusion that you wanted before in your research. So since we are looking at an association or we are testing for independency, we can say that in the first one, there is no linear relation, there is no independency or association between the 2 variables. And then the alternative or the research question is the classification. In this first one, we are setting it the other way around. We are having that 2 classifications are not independent, so there is no association. And then the H1 is that 2 classifications are independent. So after setting the hypothesis, and then you need to move on and calculate the expected values, because remember, these are counts. And when you're dealing with counts, what you get, what you're given in your data set, those are just the observed values, but you have to go ahead and calculate the expected values. Various approaches can give you how to calculate the expected values, but what is most important is that what you do in case you want to get, of course, when you go to R, they are calculated automatically, but sometimes it is important that you understand the theory such that by the time you get to the computer, everything is very fast for you to get to know that what you're feeding in is right. So the expected value is always equal to the row total times the column total divided by the grand total. Maybe in case if we had to go back here, the row totals are these ones at the end, and then the column totals are these ones that we are having, and then the grand total is what I'm having in the corner as 1,500, just as an example. When you check in different textbooks, all right, in case you want to calculate the expected frequency or the expected counts, like I mentioned earlier, what you do, you multiply the product of the marginal probabilities by n, and then you divide by the total number of observations. The marginal probabilities, if you look at whatever that we are summing at the end here, it's what we call the marginal value. So the probabilities you have to divide by the total number. But basically, what you do, you get the row I total, you multiply it with a column, and then you divide by what? The number of observations. You can check in many best statistical books and you will see that. So then step number 3, you need to calculate the deviation between the observed and then the expected. You first calculate the expected, the data gives you the observed frequency or the counts, and then you get the deviation in between. And then after that, you can go ahead and, we calculate the chi-square. We know that the chi-square, it's equal to the summation from whereby you get the deviation, that is the observed minus the expected, and then everything squared, you divide by the what? You divide by the expectation. Okay, we are also calling it also the, what we call the test statistic. This is the general formula. And you can still find these test statistics in the different textbooks. You can get it there. And we said that the chi-square supports us to test an association between two variables. So the 0ij, the I, these are the rows, and then the j's are the what? Are the columns. And O, that is the observed, and then the is there are the expected. And so we are targeting, we are looking at also the degrees of freedom. How do we get the degrees of freedom? You get the rows, you minus 1, then times the columns minus 1. That one gives you the degrees of freedom. And in case you visit statistical textbooks, you can also find statistical tables. For chi-square, in case of, depending on the distribution, in case of normal distribution, you can also get the one of chi-square. And all you need to do is that you need to be able to read out your degrees of freedom that you get in respective to the calculated value. Remember, how do we get the calculated value? It's what we derive it from here. What you calculate, you sum up everything. We're going to go in more details, and then you can read it from the statistical tables. I've already mentioned about the degrees of freedom, how to get them, okay? The rows minus 1 times the columns minus 1. In the previous example, I said it was a 2 by 3 contingency table. So it implies that where there is R, I put 2, and then where there is C, I put 3. And at the end of that, I come up with 2 degrees of freedom. The chi-square in this particular example, in case you compute all that, we come up with the 17.66 on 2 degrees of freedom. Okay, and then the tabulated chi-square, the tabulated, the one that you read from the statistical tables. For it, it's 5.99. Still, we are looking at 2 degrees of freedom, considering our alpha as 0.05. In this particular case, that is, okay. And then the alpha, that this is the level of significance that you want to consider, which is 0.05. We've been mentioning about still this alpha throughout this particular training. I guess at this particular stage, at least now we know what we are looking at. So most of the time, in case you want to come up with a conclusion, a general conclusion of whether, because by the end of the day, the result that you get, it's the one that to support you either to reject H naught or to fail to reject H naught. And the main thing in here, all you need to put at the back of your mind is that the moment the critical value, that is the tabulated value, or what you read from the statistical tables, okay, is less than the chi-square calculated, that is our test statistics. In that particular case, we reject H naught. But in case it's the other way around, then we fail to reject H naught. Okay, so this is in general what I'm talking about. Step number one, we set our hypothesis. You can say that H naught, there is no association or there's no independency. And then H1, that is the research question, or call it the alternative, you say that there is an association. Sometimes in case you're testing for significancy, depending on the level of the study you are doing, you can consider at 5% level of significancy, or you can even reduce it further to 1% degrees of freedom. Okay, when do we reject? I've already mentioned the standard one in case because it's quite interesting that also there are some students find it hard on when to reject and when to accept. But in this particular case, it can be direct forward. When you see that what you've read from the statistical table, okay, that is the tabulated, or call it the critical value. The moment it's less than the calculated, then you reject H naught. Otherwise, you will fail to reject. That is the criteria that we are going to use so far. So we are having another example. Still, I picked it from a textbook. It is saying that in 3 areas of a city, a record has been kept of the numbers of burglaries, robberies, and car theft which take place in a year. Okay, the total number of offenses was 150. That is the grand total of everything. And they were divided into various categories as shown in the contingency table. So I think right now, in case you look at this particular table, the way it is summarized, at the back of your mind, you can tell how the raw data looked like, or how the data in the data set looked like, because at least you can be able to tell, like, okay, depending on what I've covered throughout this particular week, now I can tell that having this data put in this particular table, maybe in my data set, this is how it was presented. Okay, we've got the area. In this particular case, there are 2 categories. We have the offenses and then the area. Both these 2 categories are categorical in nature. Among the offenses, we have burglary, robbery, and car theft, right? And then the areas, we have A, B, and C. Those are the cities. And we are told that we are given the counts or the frequencies in each particular case. For example, in city B, the car thefts were 14. And then in city C, robbery was 18. And then at the end of the day, we are given the totals for the respective thefts in area A, that is 55. Then 49 represents the number of thefts in area B, and so on. These are marginal additions, okay? And then the same applies to within the city. If you're considering burglary, what you're having, the 50, and then robbery, in city A, B, and C, we had 90, 23. This is the total, and so on. So whatever we are having, those are observed frequencies. But now we can move on and calculate the expected frequencies. Then from the expected, we are able to get the deviations between the 2. Then we compute the test statistics of the chi-square. Having set our hypothesis, then we want to check, can we conclude that there is an association, or the area depends on the kind of offense or not? Okay, so like what we looked earlier through the different steps of setting a contingency table, in case these are the hypotheses, number 1, you can say the narrow one, that no association between offenses and the areas of the city. And then H1, there is an association between offenses and then the area of the city. By the end of the day, statistically, we want to come up with a conclusion and check whether what we have assumed, the hypotheses that we put, are true or not. in case we are to go through the different steps, following the example that we have, remember what we are given, they are the observed one. And we saw a formula on how to get the expected values. I'm not going to go into details of that. How do we get the deviations between the expected and the observed, and then divide by the E1. In this particular case, what they're doing, they're getting the OI minus everything in this particular box. You get the observed minus the expected, and then divide by the expected, because we all have those values. And then you divide through, you come up with a deviation. But remember, in our formula, what it says that we need to sum up everything here. Okay, our I's, I say these are the columns, and then the J, they are the what? They are the rows. So in case we sum up, now this is the table. So the next thing is that we need to sum up all these particular the values that you're seeing in the third row. We're going to sum up everything and check the chi-square value that we are coming up with. So in case, using the formula that I've just shown, in case you sum up everything, we are coming up with 23.13. That is what we have. How do we get our degrees of freedom? Remember, you get the R, the rows minus 1 times the columns minus 1. In this particular example, it is a 3 by 3, okay, in both categories. So implying that in case you feed in the 3, so you're going to have 3 minus 1, 3 minus 1, and you end up with 2, 2. You multiply, you come up with 2 degrees of freedom. In case we are to take our alpha as 0.05, the level of significance. If we are taking alpha 0.05, and I would encourage you, in case you have free time, you can Google the New Cambridge Statistical tables and check. But from those particular tables, when you read the considering the 0.05 and then now taking 4 degrees of freedom, the critical value, or call it the calculated value, is 9.488. Okay, and then our calculated one is 23.13. So the point now we have to check, you know, my calculated is 23.13. And then what I read from the table, it's 9.488. Am I going to reject or am I going to accept? So let me ask in the chat, looking at this particular scenario, what conclusion can we come up with? Should we say that there is an association between offenses of the city, or we conclude and say there is an association? Please type the answer. Okay. Are we rejecting or accepting? Okay. Lina is saying that I will reject H naught. Fala is saying that we accept. So we are having 2 contradicting statements. Lassis is saying that reject, then Shahid reject H naught. Okay. Okay. Remember, the 9.488 is the value that picked from the table. We call it the calculated value. In case you read the critical, in case you consider the statistical tables, the critical value that we are having here, it's 9.488, all right? But the calculated that we got, our t-test statistics, when we calculated for chi-square, it's 23.13. Right? And we are considering at 0.05%. We are considering our alpha, the level of significance, to be 0.01. What is our criteria? What did we say? What do we need to talk about? We say that the simple criteria that we need to keep at the back of our mind, that in case the tabulated value is less than the calculated value, which I think we are having here. The table value, it's 9.488, and then the calculated value that we got, it is 23.13. So what conclusion can we come up with? Let me check again, the last bit. Yes, we are going to reject H naught. I wanted to confirm that our answers are the same. And then When you still further go ahead and reduce the level of significance to 1%, with the critical value or the value that you're going to get from the table, it is 13.28. So again, even the 13.28 is less than 23.13, which is our calculated value. Again, from the conclusion, we are going to reject H naught because the tabulated value, call it the critical one, is less than the calculated value. So we can conclude and say, depending on what we have, we can conclude and say that there is strong evidence of an association between offenses and then the city where somebody lives. Okay, let me check in the chat. Are we on the same page? Yes, I've seen the answers. I think now we've come up on the right conclusion. Can I continue? Are we on the same page? We'll see more details practically in R as we move on. Okay, there's also another question that an exercise. In case you check in the Google Drive, there is this particular example where I'd put an exercise. You can do it on your own free time and check if you're coming up with the same conclusion that I have. Okay, now, apart from checking for associations, we also say that you can use the chi-square to test for the goodness of what? The goodness of fit. So in this particular case, how does this one happen? Under the goodness of fit, this one is used to test if the hypothesized proportions given by the null hypothesis fits the what? Fits the data. So what is the trick here? The example is that suppose a random variable of size n is classified in 2 K categories or cells. We are only dealing with a random sample of size n, and it has been given the respective what? The respective categories. So now for us to use the chi-square to test for the goodness of fit, how are we going to get the degrees of freedom? It is going to be K minus 1 degrees of freedom. In this particular case, we are only dealing with only one variable. Yet initially, we are dealing with 2 variables. Okay, so how do we do that? In here, what we are going to do, we are having a very simple formula that we are going to use. The test statistic, we need to calculate for the goodness of fit. And this one applies if you're dealing with a discrete random variable, okay? So we are saying that for a discrete random distribution with K categories, all right? You're having the observed frequency and then the expected one. So this is the formula that you use. And then the same, the chi-square is K minus 1. You get the number of categories, you minus by 1. In case there are 5, when you minus by 1, your degrees of freedom will be 4. In case there are 2, then you minus by 1, your degree of freedom will be 1. Right? So, and then we are trying to check whether the hypothesis that we are set is whether it gives a good fit or not. And then it's also important to understand how do you get the expected frequency in case you're dealing with a goodness of fit test. The EI, which I'm calling the expected frequency, in this case, it will be equal to n times 1 over k. Remember our k, these are the what? Are the categories that we are having. So we'll be able to come up with the expected frequency. I don't want to go into these details here, but all I want us to understand, in case we go to R, how do these things work out? Theoretically, we can keep this particular example for a case of the goodness of fit. And the question is, we're having a confectionery company is trying out different wrappers for chocolate bar. Okay, we have its origin, A, the 2 newer ones, we have B and then C. These are wrappers. They had the original one, and then they want to test the new wrappers and then check whether, it puts the bars on display in a supermarket and looks to see how many of each wrapper type have been sold in the first hour. We are given results. That wrapper type A, the original one, they observed that there were 8. Then the B1, there were 10, And then the last wrapper C, in the first hour, they were what? They were 15, and giving us a grand total of 33 customers. So the question at the back of the mind is that in this particular case, we are having only one variable. This variable, that is the wrapper type. Within the wrapper type, they've got A, B, and then C. And these are the different wrappers that are being displayed. And they are trying to see whether when customers set into the supermarket, the different wrappers will influence their decision. And so we are given the numbers, those are the observed frequency. So now the hypothesis or the question that we need to have at the back of our mind is that, is there a difference between wrapper types in the customer choice made? That is the question, because by the end of the day, in case there is a difference, then that one will influence somebody's choice. In case there is no difference, then that thinking will also influence somebody's choice. So what do we need to test? We are asking that, is there a difference between wrapper types in the consumer choice made? All right, so that is the question we are asking. What are we testing? We are testing the difference in preference for the wrapper types. So H0, there is no difference in preference for the wrapper types. And then the research question, H1, there is difference in preference for the wrapper types. Remember what we said, in such a scenario, we need to test for the goodness of fit. We only have one variable. We've got the observed frequency, we need to calculate the expected frequency. Expected is equal to, in case we go back just one slide, is equal to n, then times 1 over k. Our n, that is the sample size we are having, the total number of observations, and then the k, these are the what? The levels. So let's move on and see. So checking here, the choices, that is the k, there are 3, and then the total number. If you go back here, our n is 33. That is the sample. Those are the customers that we had. So calculating the expected frequency, in this particular case, it's 11. So now, after this, we go back and fit in our general equation here. We have from 1 to k. We have 3 observations. We are going to move from the observed, the A type, and then the B type, feeding in there. So what is going to happen is that in this case, we are going to get the first group. In case of the original, which was 8 minus 11, everything squared, we are feeding into the formula. And the calculated value we are getting, it is 2.364. How do we get the degrees of freedom? It is k minus 1. How many levels do we have? K is equal to 3. So in case you minus 1, you come up with 2. So you can test on the different levels of significance. You can check at 5%, you can check at 1%, you can also check at 10%. So what happens at 5%? Let's check. At 5% significance level, in case we are considering our alpha as 5% and our degree of freedom as 2, all right? If we read from the statistical tables, the critical value or the tabulated value is 5.991. But the calculated one, remember, it is 2.364. So what are we going to do? Are we going to reject or we are going to accept? This time around, the table value, it's less than the calculated value. Let me check in the chart. What conclusion are we going to give in that particular case? What conclusion are we giving? Okay, Zofa is saying that we accept H0, Abera that we accept, Doris has also mentioned that we accept. Can I get more answers? Okay, accept H0, do not accept. So we failed to accept H0. Great, thank you. So in this particular case, we are not going to reject, we are going to take up H0. We cannot reject H0. So the point is that in this case, we are not rejecting H0 since the calculated value is less than the tabulated value. So you can do the same and come up with a conclusion. What if you're considering 10%? In case we are considering 10% as our significance level, the critical value is 4.605. And still we can see it's the same story, whereby the tabulated value is greater than the calculated value. So we are still going to come up with a similar conclusion. So in this particular case, the conclusion that we are going to come up with that we don't have enough evidence to show the strict preference in the particular lab was based on the choices of the customers in the first hour. All right. Okay, this is another example, but it's the same information, or it's the same criteria that we are going to use. And so within example 2, they're saying that many people believe that when a horse races, it has a better chance of winning if it starts lining up position is closer to the rail on the inside of the track. The starting positions of 1 is close to the inside rail, followed by position 2, and so on. The table below lists the number of wins of horses in the different starting positions. Do the data support the claim that probabilities of winning the different starting points are not all the same? That is the question that we are given. What we are having, the starting position, and the different positions run from 1 to 8, and then the different wins that are scored by the horses in position 1 up to position 8. Also here, we want to test the goodness of fit, and we want to test whether there is a difference in position for winning or there isn't. And so we do the same thing. And for us to come up with the total N, what we are going to do, we are going to sum up the total number of wins. Okay, and in that particular case, we are coming up with 144 to come up with the expected frequency. Remember our formula that EI is equal to N times 1 over K, the level of categories. In this particular case, when you count them, they are what? They are 8. And then now we continue, we do the same like before. So in here, these are the calculations that are being made. We have the observed. We can now be able to get the expected, then the deviance between the two, and then this last line gives us the test statistic. And when you calculate it, you come up with 16.34 because you need to sum up everything there. Okay. We still use the same terminology, whether we are rejecting or we are accepting. What do? We still go back at 5% level of significance and check what will be our calculated value. In this particular case, the degree of freedom, it's K minus 1. They are 8, we minus 1, we are having 7. What we are saying is that the critical value or the tabulated value is 14.067, and then the calculated is 16.34. So it's still in this particular scenario. It's like the one we encountered in the first example, whereby the critical value is the critical value which we are having as 14.067. That is the tabulated value is less than the calculated value. And I remember in this particular case, we rejected the null hypothesis. And so, and also you move on like that, depending on the question that you're having, then all you need to understand is that what am I exactly supposed to do? How do I test my hypothesis? When am I supposed to accept? When am I supposed to reject? Those are the important things. There's also another example, which I'm not going to go through, but you can try it out on your own. Now we are going to move on to R and see how do these things work out. Okay, I've just checked in the chat. I'm not seeing any question. So I'm going to stop sharing this and then and I open. Please check in today's work for day 6, and then you'll find the data set that we are going to use, which is categorical data R. I'm not going to cover that. You're going to answer? Okay. It's fine. Okay, let's continue. We are going to use the data set. We know the work salaries data set. You can check again in that same folder for categorical data. I put the same data set, but we also had it for day one, so you can still check. So under, in case we're going to perform for the case of categorical data, we need to run these libraries. I'm not going to install any of these libraries because I've already installed them on my computer. So all I need to do is to run them. So also go check in your folder, whatever folder that you're using in this particular training, and then go ahead and open the categorical data.r script on your computer, and then we work out together. So what we are going to do here, I'm going to load my libraries. It is always important that as you move on to R, all right, as you go to R, whenever you're going to do any data manipulation, any statistical test that you're going to do, to ensure that you load the required packages. In some of the different comments I've been seeing in the Q&A, where you're getting errors, or my code, a certain line is not running. Most of the time, in case you did not load the packages, because all the functions that you need to run those the different commands are built in these particular packages. When you are installing a particular package, you need internet. But after that, you don't need any internet. You just load and use. So I want to import my data in R. In that case, we looked at setting the working directory. So I want you to import data into R, and the data that I want you to import, which still is already in that particular folder, day 6, it is called the work salaries. So in case you import it successfully, you should be able to see in your environment that it has been loaded very well. Let me first clear. I make my work a little clean, such that people might ask me questions that are not part of what I'm talking about. Okay, I want to run my data. I want to import my data in R. So I'm importing work salaries.csv. Can you please go through that? I think at this particular stage, I believe now majority of us can be able to import data into R. So let's import our data into R. We are importing the salaries data set. For you to check that you've been successful, you have to check whether the data has been read in the environment. Otherwise, you're going to come up with a red line or an error. R will complain that maybe you've not set the right working directory. Okay, let me check in the chat. Okay. Have you been able to import the data? Okay, Adam is saying yes. Mona, wow, great. Can I get more people? Done, that's wonderful. Okay, so remember, in case you're not using inbuilt data that is in R and you're importing data somewhere to R, you need to ensure that you use the right steps. Otherwise, you will not be able to work out anything. It is always important that you look at the structure of your data set. And in this particular case, we discussed this earlier. So I'm going to just continue. We have rank, discipline, years since PhD. We have years.service, 6, and then the gender. And we've been mentioning about, in case you're having a data set and there are some variables that must be categorical. So what you do, you have to tell R that convert these variables into categorical, such that when you continue with analysis, they are read in that particular case. So in here, I want R to read rank, discipline, sex as categorical variables. So I use as dot factor. In a different scenario, I've seen Thomas using factor. It is the same thing. There is nothing that will change. So I run that line, I run again, I run also the sex. Then in case I run again my structure, what is going to happen is now going to show me that my rank has 3 levels, discipline has 2 levels, and then sex has 2 levels. So in here, it implies that I've been able to run my data the way I want it to look like. So I can proceed, because what is our main aim here is that we want to check a chi-square. And with a chi-square, what did we say? We need 2 categorical variables, all right? And check if there is a relationship or not. So what I did here, I thought that maybe since salary was our dependent variable and it is continuous in nature, but there's a possibility that you can convert a continuous variable or a numerical variable to categorical. I remember talked about this command. I don't know whether it was on Monday, and we've been talking about how these commands are. You can get a summary of your data set as a whole or looking at a specific variable. So in here, in case I take a summary for salaries, then $ salary, what I'm getting, when you check down here, I'm having a summary statistics over the different points, the minimum up to the maximum. I can create a test condition by using an if-else command, such that in case I want to categorize salary, using into 2 groups, low and high. So I use the if-else command. I'm moving a little fast because I've already discussed this part, I think, in the training earlier this week. So in case I run this, if I run that, it is showing me. Then I want now to view my salaries and check whether it has worked out for me. Yes, I covered it in data manipulation. I was looking at the specific point where I talked about it. So here I'm having salary, and then now I've created a new variable, which is salary cut. And here I'm having two levels. I've got the high and then the what? And then the low. Great. Now, what happens in case you want to look at an association between 2 variables? We remember the first thing, what is important is that we can first run a cross tabulation of 2 categorical values. Initially, we were using, for the case of the 1 variable, we're using only the table command. For example, here you would say salaries and then rank. If you remember, for only 1 variable. So we are using table, and then the moment you run that variable, you would come up with the different labels for associate, the assistant prof, and then the professor. But now this time around, because still there are 2 categorical values, what we are going to do, we are going now, instead of only 1 variable, we are going to create a comma and then add in another variable, another categorical variable. For example, if you look at this particular line, okay, in case I copy it and I first write it there, when you look at it, this one is table. I want to look at if there is an association between rank and the salary cut. Here in the above line, I've got table salaries and then rank, okay? In case you also want to see the salary cut, you can do the same and type table, and then you say salaries, $, what do you want? You want to check for, this is only 1 variable. If you run it, you're going to say that those who belong to the high category, it's 168, and then in the low category, it is 220 9. That was for only one categorical variable. But now in this particular case, what about in case you want to create two variables together, a cross tabulation, or you can call it a contingency table? In R, what you do, you add the other variable in the same line, but what you do, you create a comma. So here I can run this particular line, and what I get now, it is the cross tabulation of the two variables, rank and then a salary cut, but they're both supposed to be categorical. So the frequencies that we are getting, I'm having the associate professor, there are 3 in the high category, and then 61 in the low category. I've got 0 in the high for assistant professor, and then 67 in the low category. When I look at the professors, I'm having 165 in the high category salary and 101 in the low salary. We've been talking about creating an object. In this particular line, I'm using my table as an object. I can still run that because I want to store my information. And then for me to see the result, I run that line. So it is the same result that I'm getting here. Okay, remember, we can add the totals with what we call margins. So whereby here, I can get the total number of associate professor that belong to the high and low category. I can come up with the total number of assistant professor that belong to the high and low category. How do I do that? I get another command, another argument. I use a command which is called add margins. Okay, in adding margins, I tell R, I want to add margins in my table, which I call my table. And remember, for the case of the margins, these are the total rows and then the total columns. The one for the rows and then the second for the what? For the columns. So in case I run this particular line, I'm getting the totals, what I asked for. The margins, I'm having 64. That is the total. They are getting high plus low for associate prof, which is 64. When you come to professor, I'm getting the total for high, 165. Then I add 101 to come up with 266. In case I want only the high category, okay, for the different ranks, I get 3 plus 0 plus 165, and you come up with 168. Okay, when you come to the low category, still these are the sums. There's some, I'm having sums row-wise and then column-wise. This one is the column-wise in case I'm going horizontally, and then the vertically, I'm summing column-wise. So those are the margins that we had, if you remember, within the slides that we looked at. It's also important that you can be able to get the different proportions. So, or they call them the percentage, because in this particular case, what I'm having are the frequencies. So in this case, if I'm to run, I'm using a command prop.table. So under prop.table, in case I run that, I get the different proportions. For the associate is 0.0075, and then that is high. And then when you check in the case of the professor belonging to high, it is 0.25. All right. So how do I run a chi-square? It is very easy. I run a chi-square between two categorical variables, and I'm using what we call a chi-square test. In R, it is the chi-square.test command. Remember, R has got a help function. In case there's something that you need more clarity on, you can type question mark chi-square test, and then you read about the different details that can use to support you to understand more what exactly that you want to. So here, I say that I want to get a chi-square test between rank and the salary cut. So my assumption for the H note is there is no association between rank and salary cut. And then the alternative is there is an association. But most of the time, in case we come to R, we are trying to test against our alpha, which is by default 0.05. How would our p-value look like, such that we come up with a conclusion whether to reject or accept the null hypothesis? Okay, in case I run that line and you check in my console, what I'm having is that the chi-square value is 128.62. My degree of freedom is 2. Remember what we said, that is R minus 1 and then times C minus 1 for us to come up with the degrees of freedom. In this case, I've got my rank. It is my rank. I've got there are 3 ranks, and then with the and then with the salary there are 2. So with the 2 minus 1, I come up with 1, and then 3 minus 1, I come up with 2. I multiply, I come up with 2. Overall, my p-value that I'm getting, it is 2.2e to the power minus 16. So let me ask in the chat, basing on the output that I'm having, what conclusion can you come up with? What conclusion can you come up with? We've come up with a chi-square. This time around, we are given the p-value, okay? We reject H0, reject H0. Doris is also saying that we reject H0. Do the rest agree with the conclusion that we are having? Okay, salary has an association with rank, great. Okay, so we reject and then we take the alternative. And yes, salary has an association with rank. So thank you so much. Depending, looking at the conclusions or the comments that you've given, we are saying that we are going to reject H0 and then accept our research question that there's an association between rank and the salary category. What is important? You need to understand the command, what we are using, and then inside the command, you put the 2 categorical values that you want to, variables that you want to check whether they are associated or not, all right? And this one, what about in case we are looking at sex and then the salary card? You can also come and run on this particular line. Remember, by default, we are considering our alpha as 0.05. When you run that, we are given the chi-square as 2.916. And then this time around, we are told that the p-value is 0.08767. So in this particular case, what conclusion can you come up with? What conclusion? So we accept H0, all right? Any other? Accept H0. There's so far 1 person. So we're accepting H0, the same as fail to reject H0, accept H0. Wonderful. I'm glad that now we can make the right conclusions. So basing on the conclusion that we are having here, in this particular case, we are going to accept H0. Somebody has said accept H0 is the one who is the same. It is similar to one saying that we accept what? H0. That in this particular case, there is no association between sex and then the what? The salary cut. In here, I've been using salary cut because it has been the dependent variable, but it doesn't matter. You can also look, you can also go further and look at an association between the variables themselves and then check. What do I mean? Let's take an example. Assuming maybe I want to check if there is an association between rank and the discipline. Let me put discipline, and we see whether among us now the var, because it is a generic command you can keep using and apply it. Then okay, let's check and see. So what we are saying that in case you're checking the association between rank and then somebody's discipline, so it is saying that my p-value is 0.09, which is greater than 0.05. So in this particular case, from the conclusion what we've been making, we shall conclude that there is no association between rank and then somebody's discipline, and so on and so forth. That is how we deal with categorical data. The point is we can test for chi-square. In case you're dealing with only one variable, you can go ahead and check for the goodness of fit. Well, what we are doing here is that we are giving you the basis or the ground for clear data analysis, because the point is that You need to understand the principles. From the basic principles, you can actually go and do a lot and a lot more from what we are having. Okay, let me check in the chat. We are still having the answer. The salary is not associated with gender, accept H note, and then we accept H note. So those are the answers that we are having. So I'm going to stop here. That is the part that I wanted to share on categorical data. But like Professor Susan said, please practice, practice. After getting this knowledge, apply on your personal data. Otherwise, if you don't, you're going to forget these things and it won't make sense for you in case by the time you get to analyze your work and you've forgotten the various commands that you need. All right, I'm going to stop sharing that and then I move on to something else. Okay. Any questions or I proceed? Can we what? Yeah, but it depends on the variable that you're looking at. Okay. Okay. I want to move on to generalized linear models, and specifically, I want to first look at logistic model because they're the common ones, use the one, and then we see how can we, in case you, when are you going to use a logistic model? Let me ask in the chat, are we on the same page? Oh yeah, people are saying proceed, continue. Great, let me continue. At least now we've achieved the concept of categorical and when are we supposed to see it? When are we supposed to use a chi-square test? That is wonderful because by the end of the day, as you are doing your various research, it doesn't matter the field that you are in. At one point, as you're proceeding in analysis, you need to check whether your variables are associated or not. Okay, great. Now let's move on to logistic regression or logistic models. They are under generalized linear models. Initially, in regression, what Prof was looking at in regression, the linear and then the multiple, those we refer to them as linear models. What about the generalized one? What makes them different from the linear models? Okay, so the overview, what we are, well, it is always important to understand the basics, okay? And then we are going to look at how do we interpret the result, because by the end of the day, what you feed in you can feed whatever information you have in your computer, but the point is that can you really interpret the results? So let's first understand some basics, all right? Because we are all from different backgrounds. And then this one is going to support us when we are interpreting the results. Okay, so under logistic regression, still we are going to see, based on the data set that I have, when am I supposed to apply logistic regression? Like initially when we looked at regression, if you've been very keen, when we are introducing, we said, after understanding your data set, that is the structure of the data set you're having. It is the one that is going to guide you on the right statistical method that you're going to use or the right statistical test. And from there, it will give you, you'll be able to do the right interpretation. So among the basics that we need to understand is a probability. And we all know that probability is this, I mean, it's a risk, it's a chance that something or an event will happen. All right. And we all know that probabilities range between 0 and 1. Now, the new term that maybe what we are introducing is just odds, the probability that an event will occur, okay, divided by the probability that an event will not occur, okay? Something will happen, something will not happen. So that is the odds. So in case, for example, if the probability that an event will occur will be pi, okay, then for it not to occur, it is 1 minus the occurrence to come up with the non-occurrence. If you can put it in simple terms, if it is 0.8, that's the probability of occurrence, then for not to occur, it's going to be 1 minus 0.8, and you come up with a 0.2. So implying that in this particular case, if you're to come up with the odds, we are going to come up with a 0.8, then divide by 0.2. That is the basic or the important concept that we need to pick, because we are going to go further and then apply it in a logistic regression. This is what I've just mentioned about the odds on event. You get the probability that an event will occur, divide by the probability that an event will not occur. All right. Okay. And a simple definition in this particular case, when you're looking at the odds, it's either, most of the examples that you can look at, it's a yes or no. The pi, that is the probability of yes, and then the downer one, 1 minus pi, that is the probability of no, or probability of success over the probability of failure. All right. And so we read this as the odds of yes, because most of the time we are looking at the success or when something will happen. And the moment we get that, automatically we are able to get the opposite. So we read that as the odds of yes, when something will happen. So here, what I was doing, it's just, I know that these are the odds. So just making odds the subject, you come up with that. So it is always important that the event that has the highest odds is considered to be the favorite. And then the one that has got low odds, it's the one that whereby the event is not likely to occur. For example, you can say that the odds of price uptake, that is what we are interested in. So in this case, it's the probability that the diamond price is high to the probability that the diamond price is low. Okay, we are looking at two things. Yes, no, high, low, good, bad, like that. Okay, here is a summary which we can look at just briefly. We've already mentioned that in case your dependent variable is categorical and you're also having your independent variable as categorical, so you can do a logistic regression or a chi-square test. You know, it's the same thing applies. In case your dependent variable is categorical and your independent is continuous, still a logistic regression will apply. So this is the part that I'm mainly interested in this particular session. So why and when do we use logistic? Okay, so here there are many important topics that are related in case you want to use logistic regression. But what is important in this case, we're going to look at binary logistic regression. And in here, we are only going to apply, it only applies whereby your dependent variable has got to outcome, or you can consider a dummy variable coded at 0 or 1. That is a dummy variable. And I guess when Prof was discussing about indicators under regression, you are able to say, how do we write out dummy variables? Or you can say a 2 output, did not vote or 1 voted, right? Okay, so looking at this particular slide still, with a binary response, we expect that there are only two responses, not more than that. If I'm considering my Y as whether somebody smokes or doesn't, that is the non-smoker belong to one category and then the smoker belong to the other category. I don't have any other possibility. The same story in case I'm looking at the success of the treatment, either somebody survives or somebody dies. By means two responses. Okay, so as we move on, we are looking at already mentioned about the proportion of success when we are applying a logistic regression. There are some things that, well, with the binary response, I've already talked about the binary. This is the dependent variable, 2 variables we expect, or 2 outcome only. Okay, so most of the time, in case your dependent variable is continuous, then in that particular case, what should get at the back of your mind is that we cannot use a logistic regression in that particular one. Then you need to know what exact regression are you supposed to use. But we can work with only one quantitative predictor or dependent variable, or you can have many depending on what you're having. So looking here, for the case of the regression, with simple linear regression, we had our y, which was equal to beta naught plus beta 1x, all right? The whole of this, but whereas with the logistic regression, the logit form is going to appear like this. Your y now, the dependent variable, it has got to outcome. We have the pi, we have the probability of success, then the probability of failure. And so I'm having the odds here, the pi over 1 minus pi. And we call this side here the logit, the link function. This link function, it is linking with the different predictor variables. They can be qualitative or they can be quantitative. At the same time, we can still be able to calculate the probabilities, in this case, making my pi the subject. So what you do, it's just to put natural logs on both sides, and then you come, that is how that exponential will come about, okay? Like that, so that is a natural log. Initially, this is just for a case of a binary simple logistic regression. In this particular case, we're only considering one independent variable, but it can be more than that. We can have multiple of them, x1, x2, up to xk, where it doesn't matter whether they are continuous or they are categorical in nature. So most of the time, the logit function, it is in an S shape, okay? I've already mentioned about that. I don't want to repeat it again, whereby we are looking at, we assume that there's a linear relationship between the predictors and then the log odds. That's the reason as to why I said it is important to understand what a log, what an odd is. Probability of success over probability of failure. We are taking the log odds. Also, the other way on how we are going to interpret our values that we are going to get is to understand what an odds ratio is. So this is another common way of comparing groups, and it looks at the ratios of the odds. Remember, for the odds, we say that a success over failure, depending on a group. So in this particular case, if you are looking at odds ratio, it implies that we are looking at the ratio of the odds. The odds themselves, they are ratios, but now we go further and look at the odds ratio. So we are comparing the ratio between odds for group 1 and then group 2. We're going to say, how does that help us? Also, in case you look at the odds ratio, in case the odds ratio are greater than 1, like I mentioned earlier, that this one indicates that the condition or the event is more likely to occur in the first group, that is greater than 1. And when it is less than 1, then in that particular case, we shall say that it is less likely. Remember, when we are looking at our odds, we start with the success, that is the group 1 over the failure. In case you can look at that as group 2. So most of the time, as we are going to come up with our conclusion, we are going to check what are we referring to. Is it that it's more likely to occur in the first group or less likely? Those are some of the terms that you'll encounter as you're reading further. Okay, so when we just a little theory of logistic regression, it is also important. There is also some transforming from the bounded and then to the unbounded. All right. So under probability, we say that probabilities, they lie between 0 and 1. And then for us to get the odds, you get the success over the failure. So in case my probability of occurrence is mu, okay, that an event will happen. And then, so I'll divide by 1 minus mu. How do I bring in the odds? I just need to get the log odds, and then I feed in what? My log, right? It is the same thing when somebody says that the probability that y is equal to 1, if my y is a success. And so the odds will be probability of success over probability of failure. So still from there, I can be able to come up with the log odds. Within probability, I'm saying that they are bounded because they lie between 0 and 1. But what we can do within logistic regression, if you remember, we said it was in a sigmoid form. So it starts from minus infinity to positive infinity. So we can be able to move from bounded and then to unbounded. So for example, if I assume that my mu is equal to 1, all I need to do under the odds is I just get 1, then out of 1 minus 0, and I come up with, that will give me an infinity. And when you take the log of inf, it is still that. In case you take 0.5 and you do the same, I'm trying to get the odds. Remember, with the odds, it is the success over the failure, which is 1 minus the other. And this one gives me 1. When I take the log of 1, I come up with 0. So what about in case it is 0? So my odds here will be 0 over 1 minus 0, which is 0. And then by the end of the day, when I take the log of 0, I come up with minus infinity. So when you're looking at the bounded, in case you're looking at the case of probabilities, I'm saying that they're bounded between 0 and 1. But as you go into odds and you take the log odds, you can be able to unbound. And now this time around, you start moving from minus infinity to infinity. Okay, now let's proceed. So this is just a simple equation for a simple logistic regression. So like, if you remember very well how we are writing a simple linear regression, of course, this particular side still remains the same. What is making the equation different? It is only the link function, which is the log odds. And remember, here we are having the probabilities under the odds that we are trying to get. So in here, I'm looking at a scenario whereby the log odds is a function of gender. And in gender, I've got either whether somebody is a female or the other is a what? Is a male. That is 0 and then 1. So in case I come and feed 0 here where there is gender, then it implies that the whole of this part will collapse and remain with only B. So that is my beta naught. So my intercept will be equal to the log odds that I'll get. Okay, and then in case I feed in 1 here, so it depends that it implies that now in this particular case, my log odds will be equal to beta naught plus beta 1. The betas, these are the regression coefficients that which we can find, the estimates that we've been seeing before. And it's the same thing that we can still go further and calculate them, and then they support us when we are explaining the output. I've said that the beta naught and the beta 1, these are the estimated regression coefficients, and we can do them in R and get the result. It is very important to understand that your response variable, it's if you're going to use binary logistic regression, it's supposed to be binary in nature twice, yes or no, rain, did not rain, like that. And then in this case, in case we're talking about the explanatory variables, it doesn't matter when it comes to explanatory variables, or call them the regressors or the independent variables, whether they are continuous or whether they are categorical, still you can further go ahead and do your logistic regression. So from what I just explained earlier, I was looking at gender, male for 0 and then female for 1. It is this one here, what I just explained. You put a 0, like the same similar concept we're using in regression. You put, if you put your gender 0, that is implying that that is the male, it is 0, and then the female is 1. So in case you feed in here your gender 0, look, we are remaining with only the log odds and our intercepts at 0. So how do you interpret that? And we are considering uptake of e-commerce as our response variable, so implying that either the yes, that is people take up e-commerce, then no, they do not take up e-commerce. So the interpretation that we are going to attach here, having put our gender 0 and remain with only beta naught. So this one means that the log odds of uptake of e-commerce among male students, because we put our gender to be equal to 0. Our mu out of 1 minus mu, these are the odds uptake of e-commerce, that is the success, okay? And then we've got the log. So the log odds, we are going to look at the log odds of uptake of e-commerce. Since the gender is 0, so we'll indicate that as what? We'll look at that as the log odds of uptake of e-commerce among male students. And then in case we put 1 here, now it is going to change. So we are putting the females. So we are going to read the log odds of uptake of e-commerce among female students. And that's what we are having here. Okay, so like I mentioned that from the log odds, we can be able to go ahead and get the odds ratio. How do we do that? We just take an exponentiation of the log odds, and then we are able to come up with the odds ratio. But in R, it is very easy. You can easily do it, and you can quickly put an exponent command, and you come up with the odds ratio. Let's take a brief example. In this particular example, we are looking at the relationship between treatment and then the pain relief. Okay, so my response variable is pain relief. Either somebody gets a relief or somebody doesn't. We've got two groups, that is the yes or no, the group that gets a relief and then the other doesn't. And the explanatory variable we are categorizing two treatments. We have the TMS and then the placebo treatment. And all these, they act as treatment for migraines. That is a serious headache. Okay, what we are going to do, it is interesting. This is the table that I'm having. My response has to whether somebody gets relief or doesn't. And the treatment that I'm considering, I've got the TMS and then the placebo. Remember what is important for me to calculate the odds ratio. First, I need to get the odds from the two groups, the different groups. And then later, having gotten the odds from the two groups, then after I get the odds ratio of the odds that I've gotten in each group. Okay, so here, the odds for the TMS, this is the treatment. So what is it going to be? Under this, I've got two groups. The one that says that it got relief, and then the other that did not get the relief. So it is gonna be 39 divided by 60. Those are, remember our odds, yes over no. So these are the odds for the TMS treatment. We are going to do the same thing for placebo, and we're going to get 22 out of 78, and we come up with 0.288. So how do we get the odds ratio in this particular case? We are going to get the odds of TMS, we divide by the odds of the placebo. And it's what we are having here. So I'm saying that the odds ratio will be the odds of using TMS for pain relief over the odds of using placebo for pain relief. So we are going to divide the values that we have, and we come up with 2.27. So different people interpret these results differently, but the point is, can you have a take-home message for, in case like you tell this particular result to somebody who doesn't know whether even logistic regression exists? Can you clearly communicate to this audience such that even a non-scientist is able to understand what you are saying? So depending on the interpretation that you are having, remember, if you look at what we had before, we are talking about within the odds ratio, whereby in case it is above 1, then it's more likely that group 1 will be favored. In this case, if you're looking at in terms of groups, the TM group is our group 1, because we are having the odds ratio greater than 1. So you can interpret and say the odds ratio of using TMS, okay, for pain relief is, you put the OR is 2.27 times the odds of using placebo for pain relief. I'm not using any magic. I'm just reading whatever I'm having here, what is in the odds of the two groups that I'm having. I've got those that I use the TMS for pain relief and then the placebo. So what I'm trying to say that the odds of using the TMS, because that is the group that the yes group for pain relief. So it will be 2.27 times the odds for the placebo. Or somebody else can say in a different interpretation that the people who are using the TMS treatment are 2.27 more times likely to get pain relief compared to those that belong to the placebo group. Okay. So in R, in case we go to R, what are we going to do? What we are going to do, it's very simple. We are going to go and We are going to use the GLM command in this particular. Remember, with the regression, we're using the LM, but regression is under generalized linear models. So we are going to use the GLM. Then inside the brackets, we have to talk about the data that we are basing on, like in the regression. But here, what an additional thing that we are going to do, we need to indicate the family. So the family, we are putting a binomial, or you can directly go ahead and put a Poisson. Still, you're going to come up with a similar result, because by the end of the day, the output is the dependent variable as to outcomes. And then I start with my dependent variable. Okay, here they are putting C-bind because they are putting the two groups together. But I mean, when we get to R, we're going to see that. And the output, in case you get the summary, if this is my model, in case you get the summary of my LM model, we are going to see this in R. Like we are going to come up with the estimate, we'll have the standard error, the Z value, and then the P values. We are going to come up, we will still see now output, the now divergent, we are going to see the AIC. This is just an output that it's an example that we are going to check. How do we come up with it in R? So that is what we expect to do. So here, what I was mentioning, that this is my estimate, which in the group TMS, actually, the other example that we have just discussed about the treatment where a group was using TMS and then the placebo, and they want to check whether they get pain relief, whereby we had two categories of people. One was saying that it never got, and then the other one did. So in case you put this in R, this is the output that we are getting. So one of the estimates, remember these are groups with a case of the TMS, it is 0.8184. This is a coefficient. This is my beta 1. My beta naught is minus 1.2657. And I say that in case you want to get an odds ratio, what you do, you take an exponent of the estimate in R. That is how we're going to come up with the odds ratio. So in case you get an exponent of this value here, of the 0.8184, the result that we are getting, it is 2.27. And it's quite interesting. It's what we got earlier, which was 2.27. So in case you understand how you do something theoretically, then it will be easy for you to be able to come up with the right result if you get to the practical bit. Yes, we have the two values, the probability, the p-values. You can also, they are going to be able to also check whether the variable that you want, is it statistically significant, that you can consider it as part of the decision that you're going to make or not. I don't know if I've been very fast or I've driven my concept home. Beatrice is asking that are the slides available? Yes, you check in day 6. The slides are there. Okay, Wycliffe is asking, do we then go ahead and calculate log of 2.27? No, 2.27 is the odds ratio. Remember, it was the odds of the TM group divided by the placebo group. I mean logarithm, log of odds ratio. Now we only got the odds ratio by taking the exponential of the estimate. Okay, Wycliffe, let me go back shortly and we have a recap such that that is okay. All right, it's fine. Thank you. Okay, let's go to the practicals. Maybe it will make by the time we end, we'll have it will be more clear. How many? Okay. Okay, I'm sharing my R document. All right. So still, if you check in the 6 folder, you've got the logistic_regression.r script. Please check again. All this information, you have it. And under that, still under the same folder, if you checked it very well, there is a data set which I called mydata.csv. I also sent the description of this data set. Just take a look under the description, please. Okay, let me stop sharing and see if I can share. There is a description that I shared, which you can look at. But anyway, in case you open that particular folder, and what I was trying to say that there is a Word document whereby we are looking at the description of the data set, and it has got 4 variables, whereby we have the GRE, that is the graduate record examination score. We have the GPA, the grade point average, and then we also have the prestige of undergraduate institutions. And these ones were ranked from 1 to 4. So the rank takes on values 1 through 4, whereby institution with a rank of 1 has the highest prestige, while those with rank 4 have the lowest. And then the response variable is admit, either somebody is admitted or is not admitted. So we are saying that it is binary in nature. So our goal, we want to classify students, whether a student is admitted or is not admitted. So check in the folder, there is my data set description. It has got 4 variables, the GRE, the GPA, then the rank, and then the response that has got admit or not. Okay, back to R. Back to R Studio. Okay, let me hope you're seeing my screen. I'm using the logit_regression.r. Okay, I want to clear the console and then the environment. All right, kindly, let's work together. Let's load the libraries and then we import our data. I'm using the mydata.csv data set, and then we continue from there. I guess now we are okay at this point. In case, make sure that you have these libraries, otherwise you're going to come up with errors. I don't know whether you installed the ggpubr, and then I saw you installing HMISC when you're looking at correlation. Now I want you to add for me library CART, C-A-R-E-T. It supports in logistic regression. In case you have not yet installed it, please do, using the right installing approach, and then you load it. So I'm going to run my libraries because everything is installed on my computer. Okay. After that, I import my data, depending on where your data is. Then I'm reading my data into R, and I've called it graduate. It is telling me it has got 400 observations and 4 variables. I can even view and take a look. I've got admit, which is that is my dependent variable, which has 2 outputs, a 0 and a 1. In case you have a question, please post it in the chat. Susan and Thomas are here waiting for your questions to answer them. And then we have the GRE, we have the GPA, and then the rank. What we are seeing that my dependent variable is categorical twice, either somebody is admitted, number one, that is 1, then 0, somebody is not admitted. Then the rank, we said rank is categorical, looking at the institutions, the most prestigious, and then up to the 4th one. Okay. So if I go back to R, we've already mentioned how when you can use head, I'm not going to look at that. You can run and check your structure of the data set. It is always important such that you know what you're working at. Looking at, let me first ask in the chat, have you been able to, can we have the environment and console cleared? Yes, you can. Why not? I've cleaned mine. Clean yours too. You have done that. Yes, now me, I've done it. So do it on your computer. Or you're asking how? I need to understand the question clearly. We need install please once. Yes, we install once. Then the other time what we do, we load the libraries. But please install the CAR, the CAD package. We need it for logistic regression. Install and then load it using library, then in bracket CAT, C-A-R-E-T. Make sure you're having the right spelling. Okay, let me ask, have you successfully imported my data into R? Great. Wow, this is a nice group. A jingle is still saying no. I'm wondering why. I'm just giving you a second. Bruno, post your question in the Q&A. We are not going to give you the rights of asking. Put in the Q&A. Okay, can we proceed? Can I go on now? Type in the chat. Can I continue? Okay. If that package is not installed, you're going to come up with errors and you'll be disappointed. So please, sorry? I'll be done. Okay, I understand that we've been ending at 2 and now some people are talking about what about time and so on. Okay, give me only 10 minutes and I complete this bit. Please. Only 10 minutes, I complete this bit and then we end. Is it okay? I know it's a weekend, maybe people want to go. Go for saying that, do not worry. Okay, now I'm strong, I was getting worried. Okay, let's continue. So what we are going to do, I'm going to convert admit rank to category. Please, whatever we do, also try to follow. Then I check my structure again. Now admit, it is telling me that it has 2 levels, 0 and 1. 1 is not admitted or is admitted. And then with the rank of the prestigious institutions, there are 4 running from 1 to 4. I can go ahead and get a summary of my data set, but I'm not going to explain that because it's what we've been looking at. Okay. We looked at contingency table under the categorical variables. So we said that you can use table and then inside you can put 2 categorical variables. For example, in case I run that line 33, the different students that have been admitted in the respective institutions. So those are not admitted in rank 1, they are 28, and then in rank 4, they are 55. And then the next line of 1 shows those that are what? That are admitted. Or even this line 37 can give you similar results. So it doesn't matter. For it, what it does, it just adds that on top. It just adds the variable names. the rank, and then admit, but still you come up with similar thing. Anyway, what is the main point here? So let's run a simple logistic regression. Remember, with a simple, we are only going to consider one variable. Like in the slide, we had only gender, all right? Remember, our response variable is admit. It is 2, either 0 or 1. We are looking at whether somebody is admitted or not. And then I'm only going to consider the GRE. We looked at the meaning of that. My data is what? I named it graduate, and then the family is binomial. So this is the line. I need to use the GLM command, if you remember what we had. So in case I run this particular line like this, what it is showing me it's successful, but I want to get the summary. Okay, in case I check for the summary, what is going to happen is that first it is giving me, I'm having the summary statistics, the minimum up to the maximum, but what I'm most interested in is this particular part. The beta note is minus 2.901344. You can round them off. And I'm having that all my p-values are less than 0.05. And then the GRE is 0.035. If you remember very well, my GRE, it is a continuous what? It's a continuous variable. Okay, so the question is, and this particular part I've got the log odds. So I need to ask, and this is my intercept, the beta note, and then I've got 0.03583. So how do I read that? So the way I'm going to read that is going to say that for a unit increase in the GRE, okay, the log odds of being admitted will increase by this particular factor, 0.0035882. You can do the same for the case of, maybe in case you want to use the one of, in case you want to change that, you can change the other variable. If we check properly, it was GPA. What if I put GPA? What is going to happen? I can change that, and then I run, and then also automatically my result is going to change. It is still telling me that the GPA is has a p-value which is less than 0.05. So so in that particular case, my variable is statistically significant. And what I'm having here, it is also a continuous variable. It is 1.0511. So how do I interpret that particular value? If I'm to write it out in a simple logistic regression model, I'll read that for a unit increase in the GPA, okay, the log odds of being admitted will increase by 1.0511. Right? So that is the part for only the continuous variable. What about in case I consider now the category whereby here I've got a rank. My rank is categorical in nature. Remember, under rank there are four institutions: rank 1, rank 2, and then rank 3. But like we talked about the dummy variables, within R, it will automatically pick, in case you don't tell R to relevel, that with releveling, you alerting R that consider this as my reference category. If you don't mention that, R will pick for you one and then takes it as a reference category. So I'm calling this logit 2. I'm still using the GLM, the same story. This is my data, and then I've got the family. So in case I run this out, okay, I come and ask to get the to come up with a summary. Still, what is interesting is that still when you're looking here, my rank 2, the p-values are less than 0.05, they are significant. And here I've got minus 0.7500. Then the rank 3, that is my estimate. And then R4, it is minus 1.6867. So, but what is important is that when we want to interpret our result, like I mentioned, it's good that we convert our estimates into exponential to get the odds ratio. So what I'm going to do, I'm going to, maybe let me not skip, but I wanted to take everything up. So here, in case you're seeing what I've highlighted, I've just rewritten my model again. The log odds, I'll have my intercept 0.1643. Then this is rank 2, implying that rank 1 was my reference what? Rank 1 is picked as my reference category. Then I've got I'll have different slopes for rank 2, rank 3, and then rank 4. Okay, but I want now to do the interpretation using the log odds. So let me proceed in case I come to line 56 and I call it, if I'm to consider the multiple logistic regression, if I call it my logit, and I include in all these variables that I've seen that are significant on using a simple logistic. If I run that, I've put everything, I can be able to come up with a summary of my data. When you check again, these are the combined results I get. I can be able to come up with a confidence interval. But now, how do I come up with the odds ratio? What I do, I get the exponential of my, what you're seeing inside here, this one will give you the coefficients only. In case I type there and I run, it will give me the coefficients, the betas, the beta notes. In case you check for GRE, it is the intercept is -3, that the GRE, the GPA, rank for 3, rank for 2, 3, and then 4. That one? Okay. Let's take the last bit. Now these are our odds, all right? For the case of if you look at the rank, so this one is 0.50, then rank 3, it is 0.26. When you come to rank 4, this is 0.2. Remember, rank 1, it's the most prestigious institution, and they are decreasing in that particular level. And then rank 4, it is the least prestigious. So now we are looking at somebody being admitted basing on the ranks that we are having. Let me ask in the chat, how would you interpret this value here? Our reference category is rank 1. We are looking at the log odds of somebody being what? Admitted. How will you interpret 0.5089? Let me check in the chat. Write for me the answer. Please look for. I'm telling you. Yeah. Okay, so here, since we are having our odds ratio, it is less than 1. So implying that the odds ratio of somebody being admitted in rank 1, it is less likely, there are less chances of somebody being admitted in rank 1 in case versus those that belong to rank 2. Because the odds ratio that we are having, it is less than 0.1, less than 1. So it is less likely. The same applies to rank 3. The same applies to rank 4. All our odds ratio are less than 1. In case it was greater than 1, then we would have seen that the odds of a candidate to be admitted in rank 1 maybe would be 1 times than the one in rank 2, 3, or 4. But in this case, the chances, they are less likely to be admitted in rank 1 compared to those that will be admitted in rank 2. Okay, so since people are tired, okay, within that same folder, there is Poisson regression. Kindly, in case you have time and you're interested, you can read further and then get more details. Thank you.
Hello, everyone. Before my colleagues will give their concluding remarks, I would like to thank you all for giving us this whole week to share with us the knowledge and being really, really very good participant. We are grateful that you're able to probably benefit. The time has not been long enough for everything to be covered. But with time, we are likely to go for more specialized courses. So you keep watching around, things will come. I am going to, we have your contacts. We still need to discuss with Forum the issue of certificate. So we cannot promise you, because the director is not around, we cannot promise you anything for now. But at least we have your contacts, so we should be able to follow up. We have a small study that we are going to send you later on, relating to teaching of biometrics or applied statistics in the different institutions. Your own opinion on how things can be improved. So hope once you receive the questionnaires, you will be able to give us some times and fill that one in. So we'll keep in contact. We have got the link for the Telegram, so we will join the Telegram and then the discussion will continue from there. Maybe my colleagues will say a word or two, and then we can call it off. Thank you. So Ellen, can you say some closing remarks? And then Susan will make the final closing. Thank you.
Okay, thank you. Thank you so much, Thomas. Thank you so much, Professor Susan. It has been a big journey from Monday up to now. I thank you all that you've availed your time to join us for this particular training. I'm confident that you've really achieved a lot, and you're going to apply the knowledge that you've learned in your respective work or dissertation as you're progressing on your career. I also thank the Makerere DGRT office for giving us this opportunity to train the forum executive. It is always wonderful to have this moment of training the participants. My final word, I encourage you, kindly embrace R. R is being used in all areas. So you're not going to say that because in a certain field, so you cannot use R. R is the way to go. It is a free software. The earlier you embrace it, the better. Given the scripts, please go ahead and practice and see how all this particular information that you've learned, the skills that you forgot, that you've got, how can you apply them in your respective fields? Thank you so much, and I wish you all the best.
Good afternoon, participants again. I really am grateful for having shared my knowledge with you. I'm happy that this training has come to an end, although we couldn't cover everything we had prepared, but I believe that whatever we had prepared is sort of like a stepping stone into advanced R learning. So please don't keep the notes, don't keep the scripts, practice, and practice makes perfect. Now, I would like also to thank RUForum for the great job done for organizing this training and facilitating us. I also thank DGRT, Makerere University, for also organizing this training and letting us share knowledge with you, participants. The participants have been great, excellent participants. Thank you for being patient. Thank you for, accommodating our lengthy times, especially today. And on behalf of RUForum, the staff who was around had to go and attend some urgent issue, so he's not around. But on behalf of RUForum, we would like to thank you for your patience. We would like to thank you for attending this course. And we wish you good luck in all your research endeavors. Please apply the knowledge so that you can finish on time. During studies, why RUForum decided to put up such training is that from experience, statistics has been a stumbling block in research and also graduate completion rates. That's why Reform decided to put up training so that graduate students and researchers are facilitated to complete their research and graduate studies on time. I hope this will be met. The expectation of Reform will be met through these trainings. Thank you very much. And I would like also to thank the facilitators for having endured the 6 days. With that said, I would like to, on behalf of Reform, close the training today and also extend my gratitude to participants. Thank you very much. Unfortunately, I don't have a right to give you an opportunity to say thank you, but I've seen comments in the chat thanking Reform, thanking Makerere University, thanking the facilitators. As said, the certificates will be worked on, and we have your contacts. We will contact you. Thank you very much. I think with that, we are going to close, unless if any of my colleagues have something to say. Okay, thank you. Bye. Enjoy the weekend and your great participants. Thank you very much. Bye-bye. Kwaheri. We'll see you next time. Okay. Thank you. So I am going to switch off. I will leave the training, and my colleagues also leave the training as they so wish. Kwaheri, kwaheri.